from one place to another in the nervous system. It's not chemicals either, because that would be way too slow. You can't transport a chemical from the brain to the toe in 0.1 seconds. So what is that substance? And the answer is that substance is information. So fundamentally, these pathways of neurons are there to transport information from the brain to the toes and back to the brain, of course. Okay, so if you are a cardiovascular researcher, you would want to know everything about the properties of blood. You would need to know, like, what is its viscosity, the fact that it's an Hamiltonian fluid, how much pressure do you need in order to get so much blood flow through an arteriole, etc. So you would be very interested in the basic physical properties of blood. And similarly, if you're a neuroscientist, you should be interested in the basic properties of information, because that's what gets transported through these pathways. Just as in the case of blood, you need a certain amount of pressure to get the blood to flow through a particular vessel. There are similar concepts in information theory that tell you about the limitations on the flow of information across nerves. And so that's what I want to introduce today, what these basic concepts are. And we will see that they can be applied to many different parts of the nervous system and give us some insight as to, for example, why did nature choose to build things this way rather than some other way? Okay. Claude Shannon was the founder of information theory around 1949, very influential paper. And this is the basic model for a communication process that he wrote down. He was at the time interested primarily in telecommunications as in telephone. This was a kind of rise of the telephone companies, and all kinds of new technology was getting invented in order to rapidly transmit vocal information about human voice over telephone lines. And people were very concerned in the influence of noise that might corrupt the signal along a telephone line and how to efficiently encode many phone calls into one wire, etc. And so Claude Shannon developed this framework around communication theory, which today is also called information theory. Anyway, you can kind of recognize the basic problem of telephone communication. At the one end of this pathway, there's a source. This might be a human person who's trying to convey some words to the other human person that's at the destination. There has to be some converter, some transmitter that turns the voice into electrical signals, like a microphone maybe. Then there's a cable that carries that electrical signal, and at the other end there is another transformer that converts electricity back into sound, for example, a speaker. And you have a person that receives a message at the end. So this is the kind of chain of communication that Shannon postulated. And importantly, this channel here that conveys the signal over long distances, let's say from whatever Los Angeles to New York, is subject to some noise. There's some corruption that can take place here to modify the signal so that the symbol that enters here, symbol X, sometimes gets converted into a different symbol Y at the other end. And a lot of communication theories about how should you encode messages so as to deal with these error sources and make the message robust to the error that comes from the signal. And so we can see that if you think about the nervous system, there are many cases that we can list where we can really apply this concept of communication. So let's say the synapse, right? The synapse tries to convey information from a presynaptic neuron to a postsynaptic neuron. When it does that ultimately by transmitter molecules that diffuse across the synaptic cleft, right? There is a converter here that converts presynaptic memory potential into vesicles that are released. At the other end, there's again a converter that turns neurotransmitter molecules into presynaptic memory potential, like the neurotransmitter receptor and associated ion channels. So in this way, the simple process of one neuron communicating with another neuron can really be put into this framework. You can think bigger. You can think about circuits like the retina. So here the input might be an image. The retina converts that image into optic nerve signals. The optic nerve signals ultimately tell the brain about the outside world, and the brain somehow tries to extract meaning from that. But here, the essential channel that we're talking about is the optic nerve, that transmit signals from the eye to the brain, and I'll get back to that example in a moment. You can also think about the neuron itself as a communication channel, namely the axon being the channel in this case. So the neuron gets dendritic input at one end, it converts that into axon potentials with the axon initial segment. That's a part of the membrane that produces spikes, and then the spikes travel down the axon. At the other end, there's a synaptic terminal that converts these spikes back into neurotransmitters. So in all these cases, we can see that there's a process of communication, and you can put that process of communication into this framework. Okay, so Claude Shannon's information theory has some fundamental results that really constrain how this can happen. And I want to give you a sense of the basic theory of how that comes about. Okay, at the root of information theory is this concept of entropy. And entropy is equivalent to uncertainty, right? So, for example, if I toss a coin and I look at it, you have some uncertainty about whether it came out heads or tails, right? Once I tell you, you're no longer uncertain. So the process of communication removes this uncertainty that you have about the state of the coin. Yeah? And in general, we'll see that one can conceptualize communication in information theory as the reduction of uncertainty. So let's suppose you have a random variable that has n possible values that are all equally likely. So the coin toss is an example, or I toss a die that has 1, 2, 3, 4, 5, 6 on the side, so 6 possible outcomes. They're all equally likely. I do it, I don't tell you what the outcome was, so you have a certain uncertainty about that. And information theory tells you how to calculate that uncertainty. If the outcomes are all equally likely, then the uncertainty is just the log to the base 2 of n, the number of possible outcomes, right? In the case of the coin, n equals 2, right? It can be heads or tails. And so log to the base 2 of n is 1. That means the uncertainty or the entropy of the coin toss is 1 bit. We call that the units of entropy bits. In the case of the die, n is 6, so log 2 of 6 is something like 2.5 maybe. And so the uncertainty about the outcome of the die roll is 2.5 bits, let's say. Okay, now let's take a more general case. Let's suppose that the values are not equally distributed. So for example, I might have a coin that is biased. I bought it in a magic shop, so it comes up heads 80% of the time and tails 20% of the time. Yeah? And so now there's a probability P of heads and a probability Q of tails. And what is the entropy of that distribution? And the calculation that's prescribed by information theory is that the entropy is minus P log P minus Q log Q. So you take the two probabilities of outcomes and you sum their logs like this. Okay, what does that function look like? So let's plot that entropy of the magic coin against the probability of coming up heads, P. Obviously, if the probability is 1, it always comes up heads, then you have no uncertainty, right? So the entropy is 0. Even if I don't tell you, you know it's going to be heads, right? Similarly, if it's always tails, the entropy is 0. And in between that function comes to a maximum, and the maximum is that P equals 1/2. So a coin with P equals 1/2 has the maximal possible entropy. All right, so more generally, if you have many different outcomes, and they can happen with probability Pj, so outcome J happens with probability Pj, then the entropy is minus the sum of the Pj times, this should be log base 2 of Pj. So this is just a special case of that. All right, let's take a look at an example. This is actually quite an instructive example. We'll be using it later. Shannon wrote about this in 1951. He asked, what's the entropy of English? So what do I mean by that? Let's suppose that I give you a page of text, but the last letter is missing. And the question is, what is that last letter? So you have some uncertainty about what that letter is, right? And the question is, how big is that uncertainty? Yeah, as measured in bits. Okay, so there are various ways of calculating this, and they are getting increasingly accurate. So the first attempt might be to say, well, there are 26 possible outcomes, and so I'll just take log 2 of 26, that'll be 4.7 bits of uncertainty. But that's not right? That's an overestimate, and why is it not right? So for one, we know that the letters aren't equally frequent, right? So, you know, Q doesn't happen very often, Z doesn't happen very often, and so on. So at the least, you should use the PJ, the probabilities of occurrence of the letters. And if you do that, the entropy goes down to 4.14 bits. So your uncertainty about what the next letter is going to be is really only about 4 bits. But it turns out that's also an overestimate. And the reason is that the letters aren't independent, right? So if I tell you the first 5 letters of this word, SYNBO, you have no uncertainty about what the next letter is, right? So, and then similarly, there are a lot of correlations within English, by which one character depends on the preceding ones, and that again reduces your uncertainty. And Shannon found a way of estimating that, and decided that if you just consider letter pairs, the frequency of one letter followed by another letter, it already goes down to 3.56 bits. But if you now consider words, and you look at the word frequencies, and ask what are the correlations of characters within words, you get down to 2.36 bits of information. And then you can go further, and it's actually very interesting what he did in order to find this estimate. He gave people a page of text and asked them to place bets on what the next letter is going to be. So you put down money to try to win based on the next letter. And the money was just used to get people to pay attention and make a proper estimate. And from the bets that people place, you can calculate the conditional probability of that last letter contingent on everything that happened up to now, the full page of text. And he decided that what remains in the end is only about 1 bit of uncertainty. So 1 bit is like one yes/no question. Yeah? So we've gone from 26 characters, one of 26 possible characters, to really one of 2 possible characters at the end, if you consider all these correlations within the structure of the symbol set. And this is important. So in order to estimate the entropy, you have to know not only what's the frequency of symbols, but also what are the correlations between symbols. How predictable are the symbols just from the structure of the language that's being used.
This includes also after a word? Or he always interrupted in the middle of the word?
I think he gave you a paragraph before the word, but not after the word. So there could be a bit more information. And sorry, after the letter. A paragraph before the letter of the question.
And that letter could be in the middle of the word,
yeah,
or at the end of the word?
Yeah, it could be anywhere. Yeah. Okay, so if you're interested in this, this is a fun paper to read, and in general, it's kind of remarkable. Shannon's original paper from 1949 is still, I think, one of the best introductions to this field, even though, of course, lots of textbooks have been written and so on. But somehow he had this sort of insight to compress what he was thinking in just the right amount of words, probably as a result of thinking about redundancy a lot. Okay, so far we've talked about discrete events like heads or tails, or the number on a die, or the letter of English, and so on. Many events in neuroscience are not discrete, but continuous, like the concentration of calcium, or the value of the membrane potential, or the intensity of light, etc. And so you have to ask, what if the variable in question has a continuous set of possible values? What will be the entropy? How will I calculate that? And it's really quite simple. So if you now have a continuous random variable x that has a density p of x like this, you can imagine, you can approximate this with a discrete random variable by just chopping x up into bins and then asking in each bin what's the probability of finding X in that bin. And if you make the bins fine enough, you get the right answer. This all turns into this expression for the entropy minus the integral over P of X times log P of X. So instead of the sum, as we had on the previous, instead of a sum of P log P, that sum just turns into an integral of P log P, and this allows you to calculate entropies or uncertainties about values that have continuous, variables that have continuous values. So for example, if you do this for a Gaussian variable, so a variable that has a Gaussian bell-shaped distribution with a standard deviation of sigma, you find that the entropy is something times the log 2 of sigma. So the entropy increases with the width of the distribution. Kind of makes sense. The wider the distribution, the more uncertainty we have about where the value lies. But okay, just to let you know that there is a way of dealing with continuous variables. All right, so now we know about entropy. And entropy, like I said, is uncertainty. Now we can get to this concept of mutual information, which is at the center of the theory. And mutual information tries to explain how much information the sender can transmit to the receiver. And the way it works is by considering uncertainty. So before the sender has transmitted any signal, the receiver is completely uncertain about what that signal is going to be. Right? The receiver doesn't know what X is at all. After the transmission, the receiver knows something about X, but maybe not everything, because there could have been some noise that corrupted the signal from X into Y. So there's a prior uncertainty that the receiver has about what X is going to be, and then there's a posterior uncertainty after seeing the received signal about what X was. And of course, if there's no noise, then there is no posterior uncertainty. So in that case, all the uncertainty is removed. But if there is noise, there can be some remaining uncertainty. Okay, so mutual information is just the difference between those two. The uncertainty before minus the uncertainty after, and that difference is the mutual information. And so this is often written as I of xy. So the mutual information between that signal X and the signal Y is the prior entropy of X minus the entropy of X contingent on receiving Y. Yeah? And if you take that difference, you just go through some algebra, it's all just logarithms and indices and so on, you get to this expression here for signals. Yes, this also works for continuous distributions. And so it's the sum over all possible I and j, where I and j are the transmitted and the received signals, of the logarithm of this ratio. And the ratio is the joint probability of the two symbols divided by the product of the two probabilities. Okay, so this is the final expression that Shannon produced for the mutual information that occurs between a sender and a receiver. One thing that's interesting about this expression is that it's symmetric in x and y. You can see here, if you just swap x and y, you get the same expression. And so what that means is that the information that the receiver has about the transmitted message is the same as the amount of information the sender has about the received message. Yeah. The sender also has some uncertainty about the received message because of its noise, but the information transmitted in both directions is the same. This is important also for technical reasons, because oftentimes in neuroscience we find it easier to compute the information in one direction than in the other. For example, if you're doing, let's say, sensory neuroscience experiments where you put on stimuli and then you record spike trains from the neuron. So because you're the experimenter, you control the stimuli, so you know exactly what X is, and you can control the distribution of X. You can make it narrow or sharp or wide or whatnot. You can have correlations in X. anyway, you're in control of X, and so you know everything about X. And under those conditions, it's actually sometimes easier to calculate the mutual information in the reverse direction because the h of X is perfectly well defined than it is in the forward direction where you just don't really know what h of Y is until you analyze the system better. So for technical reasons, it's sometimes easier to think about the process in one direction than in the other direction. Just something to remember. Okay, so let's pick an example. This is a sort of a textbook example, a so-called binary channel with noise. This was actually very important in the early days of telegraphy, where the signals were sent across the Atlantic by setting a voltage high or low on the transmission line. And of course, the signal decayed along the thousands of kilometers of cable. And at the end, the signal was barely detectable on the other side. And so the question was, how much information can you still convey given the decay of the signal and the noise? Yeah. And so this is a case where the signal at the transmitter can be either 0 or 1, low or high voltage. And the signal at the receiver is also 0 or 1. But sometimes 0 gets converted into a 1, or 1 gets converted into a 0 because of the noise on the transmission line. So the question is, well, how much information can you transmit that way? And if you choose zeros and ones to have equal probability, then you can figure this out by, this expression. Yeah, here x is 0 or 1 at the sender, y is 0 or 1 at the receiver, and you can figure out this expression that turns out that becomes 1 plus p log p, where p is the probability of correct transmission, plus q log q, q is the probability of incorrect transmission. And now this turns out to be the upside down version of the entropy of the binary variable that we looked at earlier. So when p is 1, meaning you always get correct transmission, then you can transmit 1 bit per symbol. Makes sense, right? The symbol has either 0 or 1. You conveyed information accurately about the symbol, so the receiver's entropy is decreased by 1 bit. Interestingly, if p is 0, meaning the signals are always flipped, this rarely happens in real life, but you could imagine p equals 0. You also get 1 bit of information transmitted because all the receiver has to do is convert ones to zeros and zeros to ones, and gets the correct information. But if p is 0.5, meaning the symbol half the time gets transmitted correctly and half the time incorrectly, then no information can pass across because the receiver, let's say observing 0, has complete uncertainty about whether the transmitted, the sender had a 0 or a 1 on the wire. Okay, so we have this kind of U-shaped curve with minimal or 0 transmission of information when p equals 1/2. Okay, so it's just an example how you calculate these mutual information for a very simple transmission system, but later on we'll talk about neurons and we'll get a bit more concrete. Okay, why is any of this useful? So far we've just talked about definitions, define entropy, define mutual information. Why does it help us? And so Shannon's information theory has a couple of very important theorems. Theory needs theorems, right? You can't have a theory with only definitions. It has to be something you can do with all those instructions. And so one theorem is the so-called data processing inequality. And what that says is that if you have a chain of events from X to Y to Z, then along that chain, the mutual information can only decrease. There is no spontaneous generation of information. It can only decrease in the context of processing. Yeah? So if I measure the mutual information between X and Z, that has to be less than the information between X and Y. Now, this sounds super intuitive, right? I mean, any intuitive notion we have of information should satisfy this, right? Because you can't spontaneously produce information about X that didn't exist here in order to inform Z. But it turns out that among all the ways in which you could formulate information theory, Shannon's definition is unique in that it guarantees this. It also guarantees that information is additive. If you have two events that are independent of each other, their entropies add, and so on. And it turns out that if you just have 2 or 3 kind of common sense requirements for how information ought to act, then Shannon's theory becomes the unique framework in which that works. This channel coding theorem is the second theorem of Shannon's theory. And this, in practice, has been the most important, I would say. And it says that if you have a channel that is noisy, so it corrupts signals every now and then, you can nonetheless produce error-free transmission through that channel at an information rate up to a certain bound, and that bound is called the capacity. So just the fact that your channel is noisy does not mean that you have to deal with errors in transmission. You can encode the signals efficiently so they become robust to that noise. And Shannon proved that there is always a finite amount of information you can transmit in the presence of noise. So who knows what a compact disc is? Hardly anyone. Okay, yeah, the old people. Anyway, music used to be on CDs, like the shiny plastic discs, and you would have to shove the CD into a slot on a CD player or so. And the music waveform was encoded on the CD, but every now and then the CD would get a scratch because you dropped it in your car and you stepped on it while driving. And you might think, well, this is terrible because now you're going to hear the scratch all the time, and it turns out not to be true. You can still shove the CD in the slot and listen to the music, and there's no scratch. And it's because the designers of CDs realized early on that people were going to step on them and make scratches, and so they encoded the music in such a way as to be robust to scratches. So even though there are now errors, some of the bits on the CD are split from zeros to ones, you can never hear those records because of the code that was being used in order to represent the music. And so at the time, in 1949, where again, Ma Bell was expanding the telephone network in the United States, this was super important to try to convey information without corruption, even though the channel itself was noisy and contained inaccuracies. Okay, the important thing is that in calculating this capacity, you have to know something about the properties of the channel. For example, what's the range and the bandwidth of signals that can sustain, what is the noise that corrupts it, and so on. In the case of the CD, you know that a scratch typically, affects neighboring tracks very similarly, and so people were able to write very clever codes to eliminate the interference from scratches. All right, so for example, we can ask, what's the capacity of the ASCII code for characters? The ASCII code is something from the early days of computer science. Who still knows what ASCII means? Yeah, the old people. Some young people. All right. So it was a code in which you could represent, at the time, all possible characters. This was before emojis, so at the time there were only 256 characters. And you can represent them all with one of 256 symbols, which requires 8 bits, 8 binary digits. 2 to the 8 is 256, right? And so the ASCII code has a capacity then of 8 bits per symbol, per ASCII character. But if you wanted to really convey 8 bits, you would have to operate in such a way that all the characters are used at equal frequency, that there's no correlations among characters. And so English obviously does not use the ASCII code very efficiently. Right? The capacity might be 8 bits per character, but as we saw earlier, the entropy of English is only 1 bit per character, so that's the most you can transmit. And we'll talk more about what that means. Okay, so, so there's this concept of redundancy. And the redundancy of a code is the amount of the degree to which it wastes the capacity of the channel. So, as I just said, English has an entropy of about 1 bits per character. The capacity of ASCII is 8 bits per character. So if you write English and transmit it from computer to computer with the ASCII code, then you're wasting, 7 out of 8 bits for every character. So the redundancy, we say, is 7/8. 7/8 of the capacity is wasted because of a poor code. So this has an important role in neuroscience. So there's a kind of normative theory framework called efficient coding that postulates that neural systems know about this problem and that they try to use the symbols they generate, like action potentials, in the most efficient way possible. And to do that, sometimes the message has to be recoded, has to be reformatted, so that it uses the action potentials most efficiently and with little redundancy. Yeah, go ahead.
How do you understand the capacity in this context? What you take? You have to the 8 bits per character.
Right, so the capacity is the maximum amount of information you can transmit using that code. And ASCII code has, 8 binary digits, right? And each of which is 1, so there are 256 possible words, ASCII words, right? And the entropy of those 256 is log of 256, which is 8. So 8 bits, but only if all the words are used in equal frequency. Yeah. And of course, that leads to a very garbled message. It no longer sounds like or looks like English if you use all 256 characters with equal probability. But that's the maximum you could transmit using the ASCII code. So one way to efficiently transmit English, and in fact, early file transfer protocols did that, is to first convert English into an uncorrelated sequence of bits, and then transmit those bits using the ASCII code between computers, and then reconvert from this very efficient code back to English on the other side. Yeah.
So, what you are here saying that the ASCII code is the kind of information. So, where is the source of noise with the ASCII code?
Yeah, good question. So here I'm assuming no noise. So there's no remaining entropy after receiving a signal, which is why I've expressed the capacity in bits per character of ASCII, right? If you transmitted it through a noisy channel like an electric wire that has some corruption and so on, then each character might get converted into a different one by accident, and then you would have to include that in your calculation of capacity. Yeah. Okay, so back to efficient coding. So if you're interested in this, it's worth reading some reviews or papers on these questions of efficient coding. If you postulate that nature has tried to use action potentials efficiently and therefore use the specific code for the action potentials, like how does a retinal image get converted into spikes in optic nerve fibers, it turns out that some of the aspects of processing in the retina can be very nicely explained based on this theoretical framework. For example, you probably know that the retinal ganglion cells have a sort of center surround receptive fields. They get excited by light in the center, inhibited by light in the surround. It turns out that this is a technique for reducing the redundancy among signals in the optic nerve. And so some of the properties of neural systems, like lateral inhibition and also inhibition over time, feed-forward inhibition, some of these properties can actually be derived from starting from the concept of efficient coding, a theory of redundancy reduction, and some measurements of the statistics of the signals that this center system has to convey. not going to go into this in more detail, but this is, I think, a very interesting branch of theoretical neuroscience. It's actually one of the few really normative theories we have that spells out that based on first principles, this is what should happen in nature, follow these principles. And it's been quite successful, not in predicting everything, but in explaining some basic aspects of how sensory systems are structured. I think in the PDF that we distributed, there are some references at the end that you can follow if you're interested. Let me skip that. This is, I wanted to say something about the capacity in the case of continuous signals, because again, many of you will be dealing with neural variables that are continuous, like memory potentials or concentration or sensory stimuli and so on. And you would like to understand not only how do I compute the entropy of such a signal, but what is known about the mutual information for a channel that operates like that. Okay, so a textbook example of a continuous channel is called a continuous Gaussian channel. And so what that means is that, variable x goes into the channel, variable y comes out, and it's corrupted by noise. And the noise is additive, meaning y is x plus n. And the noise has a Gaussian distribution. This is a normal distribution with a variance of n squared. And so we also have to put a constraint on the channel. And the constraint is going to be how much power can you actually put on the channel? Like how big is the largest signal that you can put on the channel? And for example, if the channel is memory potential, you know that memory potential has a limited range, right? It could be a few tens of milliseconds, at most millivolts, at most 100 millivolts. And so you can't put infinite amount of signal onto that channel, and therefore that constrains how much information you can transmit. And so let's say specifically that the range of the memory potential is limited to, let's say a signal range of S, and let's suppose that it is corrupted by a noise amplitude of n. So there's this random Gaussian noise that happens. It adds something to that signal that you'd like to transmit. Another thing we have to know about the system is how fast can you change the signal on the membrane. And this is called the bandwidth, or the available range of frequencies. And with those numbers, you can now calculate, using Shannon's theorem, you can calculate the capacity of that channel. And that's the maximum amount of information you can transmit. And here's the resulting equation. It's quite simple. W is the bandwidth. So let's say you can transmit signals up to 20 hertz on this neuron. Then W is 20 hertz. And then S is the range of the signal. S squared is the maximum power. N is the range of the noise, so N squared is the power of the noise. And you take the log to the base 2 of that, multiplied by W, and that's the capacity of this channel. So that's the maximum amount of information you can transmit through a continuous channel that follows these rules. And so let's take a look at what are those numbers in the case of neurons. So let me start with a second line here, which is going to be important and what happens later. So let's suppose we have a cone photoreceptor in the retina. So the signal range is about 100 millivolts. Yeah, maybe it's 80, maybe it's 110, I don't know, doesn't matter. About 100 millivolts. The noise, people have measured this by sticking electrodes in the cone and measuring how much of the wiggle around the constant potential. It's about 1 millivolt. The cones are not terribly fast. You can vary the signal in a cone up to about 20 hertz, and the reason is that the phototransduction pathway, the biochemistry that turns photons into memory potential, is a relatively slow process. There are some reactions that take a long time. And so the bandwidth of a cone is about 20 hertz. And so you take these numbers, plug them into here, you get something like 260 bits per second as the capacity. That's the maximal amount of information that the cone can transmit about the visual intensity that the light that falls on the cone. Okay, that'll be important in the second half of the lecture. Let's take maybe a more standard neuron that can operate faster. Let's say the memory time constant is 3 milliseconds. The other numbers are the same, let's say. Then you get a capacity of about 700 bits per second for one neuron. These are pretty high values, actually, compared to some of the numbers we'll come across in the second half of the lecture. Okay, so this to kind of give you a sense of what neurons can do. In the case of continuous transmission, a neuron can transmit several hundred bits per second. But of course, neurons, ultimately, most neurons fire action potentials. And so we have to ask, well, when that turns into an action potential, how much information can be transmitted that way? Okay, so let's think about the capacity of a spiking code. So this is a code where what matters is the time of action potentials. All the action potentials have the same shape, so now no longer dealing with a continuous distribution of probabilities or anything. It's just the timing of the action potentials that matter. Okay, let's suppose that the precision of the code, the precision of the timing is delta t. So the neuron can produce spikes with a precision of delta t. So for example, some time ago we found that retinal ganglion cells can produce spikes with a precision of about 1 millisecond based on visual input. So then delta t is 1 millisecond. And in each little interval delta t, there's either a spike or not a spike. If this is 1 millisecond, neurons can only fire at about 100 hertz. So that means that 9 out of 10 of these intervals are empty. And only 1 out of 10 has spikes in it because that's 1 millisecond wide. Okay, so we can make this approximation where the rate is much smaller than 1 over delta t. Yeah, again, if delta t is 1 millisecond, 1 over delta t would be 1,000 hertz. R, the average firing rate of a neuron, is much less than 1,000 hertz. So let's use that approximation. If you make that approximation, then it becomes a binary code where the spike is either 1 or 0 in each delta t. And we can again approximate that the delta t's are independent of each other, meaning the probability of spiking is independent. Under all these approximations, you find that the capacity of such a code is, depending on what the assumptions are you make about timing, can be 100 bits per second, but all the way up to 1,000 bits per second. So let's look at these assumptions here. Here I've supposed this is a typical cortical neuron, maybe with delta t, the time constant of the membrane being 3 milliseconds, and average firing rate of 40 hertz. You multiply these things together, you get 120 bits per second, about 3 bits per spike. This is a case of, let's say, an auditory neuron, where we know that this timing precision is very high, 100 microseconds or less, 10 microseconds. And they can also fire at a very high rate. And so that gives you this higher capacity of about 1,000 bits per second. Okay, so, sorry, how do I understand this? Again, you can think about it in terms of uncertainty. So let's say you're sitting here as the receiver. The sender put these spike trains on the axon. Yeah. If you look at the spiking for 1 second, then prior to the transmission, you have a certain uncertainty about what that 1 second long pattern of spikes will be. Yeah. After the transmission, you have less uncertainty. And the difference is 120 bits per second. So by looking at the spike train for 1 second, you can learn up to 120 bits. So it's the difference between uncertainty before and uncertainty after the communication. To get this, I just divide this number by that number, and so that gives you about 3 bits per spike. So every spike can tell you as much as a 1 in 8 probability. 3 bits is 2 to the third is 8, right? But for this one, it's not that dramatically higher, right? It's maybe a factor of 2 higher. Every spike can give you up to 6 bits. So what I want to point out is that here we talk about the continuous neuron, so continuous memory potentials affected by noise. And you see that these numbers are comparable, right? So 265, 700, a few hundred bits per second, right? And here we ask what happens when the spikes get converted into a spike train, and we find that, yeah, you can also convey a few hundred bits per second. So this is quite nicely matched, yeah, the capacity of the neuron as a continuous encoder with its memory potential is nicely matched to the information that can be transmitted by an axon in the form of spikes. Yeah. Absolutely, different neurons will work differently, yeah. So for one, if these numbers here are different, like the neuron has a different time resolution, perhaps. Again, here the auditory neuron has a much higher time resolution than, let's say, your typical cortical neuron. Another question is how fast can the neuron fire? And so those will lead to different estimates. I'm simplifying a little bit. There's more to be said about this. Like the assumption here is that the spikes are all independent of each other. And that's often not true. If you look at the certain spiking patterns, you find that a neuron might fire bursts, or like 3 spikes in a row, or 4 spikes in a row. So those are then tightly linked, and you cannot call those different symbols because they almost always happen bursts of heat. So to get a more accurate estimate, you have to look more carefully at the statistics of firing of a neuron and ask what are the sort of frequencies of occurrence of different patterns. But you're absolutely right that these numbers will come out different for different neurons, and if you're in Drosophila, you get information rates for neurons that are very high sometimes. If you're looking at similar synapses or similar neurons in the vertebrate, they might have lower information rates.
I think it's also to consider that because this is covered by the whole population of the calculate overall using the knowledge individually.
Yeah. Good point. So that then requires knowing something about correlations between neurons. So if you have a population of neurons in which each neuron signals independently of the others, like they talk about, for example, in the visual system, a neuron with a receptive field over here versus a neuron with a receptive field over here will have very little interaction. So they can be treated as independent signals. But if you have neurons with overlapping receptive fields, they will tend to be correlated in their spiking and produce patterns that are not independent. And so, just as in the case of English, we said the entropy is reduced because the characters of English are not independent, meaning you can predict the next character from to some extent. The same is true in the case of neurons with spiking. If you can predict what one neuron will do based on observing the others, then there are strong correlations in that population, and you have to include that calculation. So, yeah.
So actually here you use value that is R, like to represent for positive capacity for identifying. Remember, I'm using here for some words, using the distribution of ISI to calculate the quantify the capacity or inhibition functions of this component. So is there some like equivalence where you can transform from one single value R and should like recalculate for quantifying?
Yeah. Again, this is the coarsest possible calculation you can do for a spiking code. Yeah? And so it assumes that the spikes in different time ranges of density happen independently of each other, which means, as you probably know, that their ISI distribution should be exponential. This is a so-called Poisson process where spikes happen independently of each other, so you get an exponential ISI distribution. Under those approximations, you can just work with the average firing rate, because everything else is determined by the average firing rate. You know the ISI distribution is exponential. In real neurons, often the ISI distribution is not exponential. You have a refractive period. You might have excess tails in the distribution, and so on. So that contributes to what I was saying earlier: correlations between spikes. It means that spikes are not independent of each other in the spike train, and then that dependency would need to be included in the computation of the capacity. And there is an extensive literature about this. So you can read up on these methods for estimating the entropy of spike trains, both with respect to intra-spike train correlations, where different spikes are not independent of each other, but also population correlations. And I think the reference at the end might include some text. Okay, well, let me just end very quickly. So there's been quite a bit of interest in this and figuring out, what is the capacity of neural spike trains and how much information the neurons actually transmit with these spike trains. And here I sort of summarized a bunch of studies, maybe 20 studies, in different parts of the nervous system, also different organisms, Drosophila, mouse, monkey. And what I plotted here is the information rate in that spike train against the information per spikes. And of course, the ratio is just the firing rate of the neuron, right? If I take the information rate divided by the firing rates, I get information per spike. So the information rates, you can see they vary quite a bit from about, maybe 2 bits per second to 200 bits per second. The information per spike varies somewhat less, from maybe 1 bit per spike to 4 bits per spike. So this is an interesting observation that in many different species and across neurons, the information rate per spike is something between 1 and 4. I typically call it 2 bits per spike that neurons communicate. And you can ask, how does that compare to the capacity of these spike trains? And it turns out to be about 50%. So in favorable conditions, and generally this has been measured in sensory systems using sensory stimuli that the neurons are made for, like environmentally appropriate naturalistic stimuli. In sensory systems, you find that neurons often use up to 50% of the possible capacity that they have to transmit the ethologically relevant information. So I want to leave you at the end with a ballpark number of how much information should you expect spike train, and I would say the rough information, the ballpark number is 2 bits per spike. Okay, I think this might be a time to take a break. Few minutes, okay? And we'll come back and look at some of the consequences of thinking this way. So, the remaining time, I want to give a sense of very specific kind of application of this. And the question we're going to ask is, what is the information throughput of an entire human being? And so, the question is, if I put some signals into a human being and signals come out, on the other hand, what is the capacity? What is the maximal information throughput? And so let's take an example here. Typing. In the old days, my father had an assistant who would take a handwritten manuscript from him. He didn't know how to type at all. Take like a pencil on yellow paper manuscript and convert that into a nice typed document. And so obviously she's using her visual system to interpret the scribbles on the yellow paper and converts those scribbles into keystrokes. And she tries to get it done quickly. And it turns out that the expert typists can type about 2 words per second, about 10 characters per second. And we know the entropy of English text is only about 1 bit per character. And so she produces, with her typing behavior, she puts out 10 bits per second. And so we have this example of throughput where the input is some visual image with scribbles on it, and the output is typed characters, and the mutual information between input and output is 10 bits per second. Let's assume she doesn't make any errors, and she doesn't make many errors, so that's a good assumption. Okay, now you might say 10 bits per second, that seems kind of low for information throughput of an entire person. Maybe it's limited by how fast she can move her fingers, and it would be better if she didn't have to move her fingers. So here, unfortunately, I can't show this movie, but you may have seen similar movies from a competition of blind Rubik's cubing. So the competitor looks at the cube for some seconds, and then a blindfold comes down, and he quickly unscrambles the cube. And he gets scored on the total time that it takes. And the amazing thing is that the total time is something like 16 seconds. I think today's record is even better, but 5 years ago it was 16 seconds. And interesting thing about these competitions is that the athletes take about the same amount of time looking at the cube, kind of taking in the information about the state of the cube, as they take to unscramble it and putting out the information, right? So about 8 seconds of perception and 8 seconds of action in this remarkable feat. Now we can ask again, well, how much information gets transmitted in this case? So the cube has a large number of possible configurations. That turns out to be about 65 bits of uncertainty, right? If you're handed a cube and you open your eyes, the information you can glean about the state of the cube by looking at it is 65 bits. And then, of course, when he unscrambles the cube, he puts out 65 bits of information through his motor system, and that reveals then the solved cube. What's interesting about this is that he chooses to use about as much time for perception as for action. And so the concern that, oh, maybe we're limited by how fast we can move our fingers is probably not the case. He's obviously limited by how fast he can move his fingers in the second phase, but not in the first phase. In the first phase, he's limited by how fast he can take information in perceptually. And so I would argue that the rate at which we take information perceptually is limited in the same way as the rate at which we can put it out through our motor system. And in this case, the information rate is about 8 bits per second.
The first 8 seconds also is one on the internal processing, or from just absorbing information.
Sure. Yeah, I mean, visual processing, obviously.
No, I mean also computational processing of how he will solve it.
Yeah, it's probably.
So the effective time spent on just gathering information might be much smaller than 8 seconds.
Yeah, I don't know how to divide it really. I mean, obviously, there is some combination of purely visual processing to planning, maybe planning movements, or laying out an algorithm and so on. Cognition. Yeah. The point is that the first half of the process does not involve rapid movements of the fingers. And it probably involves a lot of rapid internal movements. And our argument is that those internal movements are limited in the same way, to about the same speed as the overt external movements. Okay, here's another illustration. This is a common game. I don't know if it exists in China. It's called 20 questions, where it's usually done between 2 children or a parent and a child. And the parent says to the child, go and think of something. And then I have 20 questions to try and guess that thing, but you're only allowed to answer yes or no. And so how much information can you acquire maximally with 20 yes or no answers? It's 20 bits, right? Each answer can give you the most 1 bit. And so you can gather 20 bits of information that way. So if the person asking the questions often wins this game, it means that the person doing the thinking can only think of 2 to the 20 possible things. They might take 2 seconds to think about those 2 to the 20 possible things, and so that's again 10 bits per second. So even if you consider pure thought, where you're just trying to generate the name of an object or a person or something, you're probably limited to about 10 bits per second. Okay, in this review paper we wrote recently, we reviewed lots of measurements of information rates. And it turns out that pretty much as soon as Pengcheng published his paper in 1949, people began to try to apply it to everything. And so that includes psychology. So a good number of psychologists started asking, well, how much information can humans really process? And so there are lots of experiments on this that have been done by different people over almost a century now, and done in different ways. And the remarkable thing is, if you ask what's the answer, what's the information rate in bits per second, it turns out to be 10 plus minus factor of 2 or 3 bits per second. So all these very different ways of trying to estimate the throughput of a human being end up with about the same number. And again, oftentimes the throughput is clearly limited by motion. Other times there's no motion at all. And it's just internal storage converting to memory or something like that. Okay, so to me this looks a bit like a natural constant. Like human behavior happens with a speed limit of 10 bits per second. So that's how fast you can acquire information, that's how fast you can communicate information, that's how fast you can just think internally. About 10 binary decisions per second is the way to think about it. Okay, so why is that number interesting? Well, you obviously have to compare it to some other number. And one way to compare it to another number is to ask, well, how much information actually got into the human being in the process, let's say, of typing? Well, this is where these calculations from the earlier part of the lecture come in handy, because we can calculate the information rate of a cone. And I told you it was 200 something bits per second at best. You can multiply that by the number of cones in the retina, their bandwidth, signal to noise ratio. You get something like 10 to the 9 bits per second of raw visual information that can enter the retina. And somehow that gets converted into just 10 bits per second at the output. So all this computation that happens inside our visual system, and the motor planning and whatnot, etc., takes in on the order of a gigabit and puts out on the order of 10 bits every second. So I've compared this sometimes to the 10 bits being a needle in a haystack. So the visual system starts with this giant haystack of information, pixels in the image, and it tries to reduce it to just 10 bits per second, which is sort of needle in the haystack. Another quantitative comparison I like is that it's like drinking water from the Hoover Dam. The Hoover Dam is it's a tiny version of a Three Gorges Dam that exists in North America. And but anyway, it does transfer a lot of water, and you can compare that to the rate of human drinking, and it's about that same ratio, 1 in 10 to the 8. So her finding the 10 bits inside the raw visual image is a little bit like drinking from the Hoover Dam. Now, drinking, of course, is easy. You could just bend down and sip the water like that. But it's actually maybe more useful to think of the fact that, let's say, you can only drink D2O, the heavy water molecules, in the Colorado River, because then, of course, you need a very efficient filter to pick out only the D2O molecules and the number of H2O molecules. So processing in the visual system is a little bit like filtering the Colorado River into extracting just the heavy water molecules. I use this when talking to chemists about what is the power of visual processing. Okay.
So I'm wondering how many much of the from the neural
But the information in the natural machine is actually the most big stationary and the most accurate, and it's drastically in the physical world are predictable. So the information may not be so large. So it has to be information.
Yeah. You're exactly right. So this calculated is a calculated capacity. That's the maximum amount that the retina could take in when looking at maybe a random flicker noises or something like that. But as you say, natural scenes have a lot of correlations built into them, both in space and in time. And so the actual entropy of a natural scene is much lower than that. But the visual system has to know about that in order to process it properly. So a lot of early visual processing actually makes use of this redundancy in the natural scenes to recode the image. And it's basically the first few steps on the way to extracting the 10 bits that matter for behavior. But you're absolutely right that the raw visual image, like the pencil marks on the yellow paper, is not a random dot display. It definitely has a lot of correlations. Okay, so here we've compared this relatively modest number of behavioral throughput to a big number of neural throughput in the periphery. You can compare it to other numbers. So this is a comparison to the information rates that our technology uses in communicating visual images. I was at a workshop not long ago on data compression, and there were people from Netflix there. And so we talked about what are the data rates at different stages of production of a Netflix show. And so here's an example. Okay, the Netflix show starts with a script. Some writer actually writes a story. And I've measured the information rate of that story relative to the speed at which the movie happens ultimately. And it's about 50 bits per second in that story. So then the company hires actors and cinematographers and buys a bunch of really expensive equipment and puts it on trucks and drives it to the desert and produces movies that have an information rate of about a gigabit per second. High resolution cameras, high frame rates, multiple cameras shooting at the same time, etc. Then it all gets cut into the final version, and it gets put on the internet for distribution to your households. And it turns out they're able to compress all that to about 100 kilobits per second. So that's when the Wi-Fi arrives at your home. That's about the rate at which it produces information. Then your giant screen television converts that back out into millions and millions of pixels and high resolution, all the different colors, 60 hertz per second, 60 frames per second. And so the capacity of that high resolution display is again something like a gigabit per second. And then finally, the viewer watches this and takes away a very small part of the original script at about 10 bits per second. And so these Netflix engineers were very excited by this diagram because they thought, we really want to reduce this bottleneck here. We want to reduce the bandwidth used for distribution to your household as much as possible. And so knowing that the ultimate consumer of the information only gathers 10 bits per second, is it possible then to compress this signal further and squeeze that down? And so we talked a bit about what would be needed to do that. And I think it's conceivable, but technically challenging. It has to do in part because of eye movements, so that when the viewer looks at the screen, of course, they don't take in the whole screen all the time. They're kind of moving their eyes around, and you can't predict those eye movements if you're just Netflix, unless they're wearing an Apple Vision display where you can actually measure the eye movements and could in principle reduce the bandwidth at which the signal is displayed. Anyway, there are technical complications, but I just want to point out again the enormous ratio of the information that we ultimately take out of watching the television show to the information that gets put in to producing it.
But here the tendency, if I were telling my neighbor who's not seeing the movie, oh, I see somebody on your, so it would be some action. But for example, when I read the book, it elicits a lot of imagination, pictures, emotions, and so on. And so internally, it might be much higher than this percent. So this 10 bits per second, if I summarize, something to someone, but internally it might be much higher.
Yeah, I mean, that might be made up, but
Sure.
images that you create internally are just, they're not, it's not information transmission, right? They're making.
In the case of reading, yes, but here maybe not. I mean, here you will be, reflecting small details that you see on the screen. And
yeah. So we've looked into that. So there is this illusion that we all have. It's called the brand illusion in visual psychology, that the world is present at some incredible detail, high contrast, high resolution, color everywhere, and so on. And so the objection has been, okay, I'm looking at this image, and maybe if I have to talk about it, I could only express myself in just a second. But really, internally, I know all these things that are out there in the world at the high resolution, and that's just not true. It's literally an illusion. You can do experiments where you ask people to recount what they've seen in different places in the visual scene or at different times, and our perception is incredibly crude of what's out there. The reason we have that illusion is that, in principle, we could, of course, in real time, move our eye to anywhere in the scene and experience it at high resolution, right? And so that's where the illusion comes from, that the scene is present internally at all times at this high resolution. But really, and I know Robert has done this experiment, if you look at a letter on the page and ask how many letters can I actually see to the left and to the right of that, it's maybe 4 or 5. So really very, very limited high resolution perception of the visual scene. And there are a number of other illusions about our cognition that come from the same source. Namely, in principle, I could be thinking about lots of things, and therefore we have this illusion that we're thinking about them all at the same time, that they're sort of equally present at any moment in time. And again, psychologists have done serious experiments to just show that that's not the case. We have the ability to think about different things serially, but only at about 10 bits per second. Let me move on. How much time do we have? What do you like to do?
We have 2 minutes.
Oh.
Yeah, 2 minutes. Yeah.
But
yeah.
Yeah. Keep going. We have a questions from the Xingyu. Yeah.
Sorry, we want to save time.
Okay.
Okay. Let's see. I'm going to show you a little bit about some experiments that were just started. A lot of the arguments here you can read up in this review paper we published recently. One of the questions that leads us to is if in fact our cognition happens at a rate of 10 bits per second, why do we need so many neurons? And we can understand why there are so many neurons in some parts of the brain, like the visual cortex, for the reasons we just discussed. You need a lot of visual processing in order to take the little scribbles of pencil on yellow paper and convert them into characters. A lot of visual processing is needed. And we actually understand quite a bit about the nature of that visual processing. But once you sort of reduce things down from the periphery to the 10 bits per second stream, why do we need so many neurons to operate at this low level of information rate now? Like when it comes to making decisions, or combining the 10 bits per second from the retina with maybe 10 bits per second that come from some other stream, making decisions, looking things up in memory, so on, combining with internal drives. Why does that require so many neurons? And we've kind of singled out particular area that is supposed to have to do with the control of behavior of the prefrontal cortex. In people has about 1 billion neurons, and primary visual cortex also has about 1 billion neurons. Now in primary visual cortex, there is a reasonable theory for why there are 1 billion neurons. We could make arguments. For example, there are about 100,000 columns, meaning parts of the cortex that process different visual receptive fields. There might be 100 features, visual features in each column with, say, orientation and motion and color and contrast and so on. And maybe you need 100 neurons to process each of those features. I'm just making these numbers up, but the point is, if you multiply these numbers, you get 1 billion. So there's a reasonable hand-waving theory for why there are 1 billion neurons in the primary visual cortex. There is no plausible theory for why there are 1 billion neurons in the prefrontal cortex. If people do experiments in this area of prefrontal cortex, they find that there isn't a lot of parallel processing. It seems to be serial processing, like motion planning and then motion and things like that. There are variables that represent goals and values and decisions, but there's only on the order of 10 variables that people describe being represented there. And it all happens kind of slowly. And so all of that, you just cannot multiply the numbers that come up in prefrontal cortex and get 1 billion. And so I think there's a deep mystery as to why the brain has so many neurons, especially in these areas that are supposed to deal with the control of behavior that's already kind of low-dimensional and slow. So one idea we had is, okay, at any moment in time, human being only processes 10 bits per second, but which 10 bits, of course, can change from one instant to the next. And so it's not like the typists, we're always doing the same thing. We're doing something different every few hundred milliseconds or so. Edwin Mann some time ago wrote a review of where he measured the eye movements of human subjects doing everyday tasks. He says the act of making tea involves about 45 separate acts, each act being defined as movement of an object from one place to another, or change in the state of an object. And so each of these acts takes only a fraction of a second or a second, but every time that switches, the brain has to switch into a different mode and do something else. Another example I like is driving a car. And so here I fitted myself with some eye movement glasses, so I can track my eye position while driving a car. And here's just an example of recent fixations. So there's like the distance part of the car in front of me, there's the side of the road, there's the speedometer, and so on. Every 300 milliseconds or so, my gaze shifts to a different part of the car, and therefore my brain has to do something different. Measuring the distance to the next brake light is very different from reading a sign on the highway or checking the speedometer. Completely different tasks, and somehow we're switching very, very quickly within tens of milliseconds. And so we thought maybe one can learn more about why the brain needs 1 billion neurons in these areas that control behavior by thinking about this problem of very rapidly interleaving and controlling very different ways of computing these 10 bits per second. So we started doing experiments on people by recording signals in patients who are in the epilepsy monitoring unit. So these are in preparation for neurosurgery. Neurosurgeons implant electrodes throughout the brain to try to map out where the epilepsy seizures are happening. And one can add little microwires to these depth electrodes and record signals from single neurons in these subjects in the hospital. And then we said, well, let's give them something complicated to do, like driving a car. And so my students built this video game where you have to race a car around a figure-8 racetrack, and you have to watch the gas, because when you run out of gas, you have to pull in the gas station. You have to remember what's on the billboards, instructions along the way. You get penalized for banging into the road, and you can't exceed the speed limit. So it's like driving. Lots of things to pay attention to, and you have to move your eyes around in order to make that happen. So here's an example of the point of view of a patient in the hospital using a joystick to drive this virtual car. And here are some recent eye movements, eye fixations. They look very much like eye movements during real life. And so we want to know what kinds of signals can we record from the brain under these conditions where the brain changes its task, every 200 milliseconds. And so I'll show you that these are, hot off the press from the last few weeks. One thing that is cool is that you just record a random 100 neurons in different cortical areas. They fire a lot more during the game than when the game is on. So here's some average firing rate from 100 neurons. The gray sections are while they're racing the car around the track, and the white sections are when they're just taking a break and talking to the experiment.
So where is this?
6 different brain areas, hippocampus, prefrontal cortex, IT, like visual cortex, supplementary motor area, and I forget. Anyway, they're kind of distributed around the cortex. We have no choice in those locations. They're chosen entirely by the neurosurgeons, of course. So, more firing during the game than between the game. Interesting thing is, it's correlated with the performance of the subject. If I plot the average speed of the subject running around the track, racing around the track, against this increase in firing rates, the expert subjects have hardly any change in the firing rate, and the inexperienced subjects that are performing poorly have a lot of change in the firing rate. Now, when my student first announced this, I thought she had it the wrong way around. It has to be more firing is better for performance, right? But it turns out not to be the case. So as you get better, in fact, even if you track an individual subject over multiple days, they get better at the game, and the neural firing decreases. Where expert subjects have the same average firing rate when they're in conversation and when they're racing around the track. Anyway, that was unexpected observation. Then you can look at the tuning of individual neurons, and my first expectation was, well, it'll be difficult to make any sense of what these neurons are doing, because we're picking 100 neurons at random, and we're giving this task that has many different things going on. But actually, you can understand the firing, or at least believe you understand the firing of many of these neurons already. Here's an example of 150 neurons or so from different subjects, so different colors here, different subjects, as a function of location on the track. And so these periods here are when the billboards are visible. So the subjects are looking at the billboards, trying to remember the instructions. And in every subject, you find neurons that seem to be firing selectively when that happens, during that period when the billboard is available. And then other neurons have very different dynamics. Increase gradually before pulling into a gas station, and then decrease again. So this might be a neuron that is responding to a gas tank. But we still have to try to interpret these things. The important thing is that there are some very strong signals, and they cut across subjects. So different subjects seem to be solving the task in similar ways at the level of their neurons. And then you find some odd single neuron tunings. For example, this is a neuron that fires a lot when the subject glances at the gas gauge, but not when he glances at the speed gauge. That's when firing goes down. Here's a neuron that fires in preparation for entering a gas station, but not when fires when the subject does not enter the gas station, but does not fire when the subject does choose a gas station. So these are, of course, there are hundreds of these specific tasks that occur throughout this racing game, and very frequently we can find neurons, individual neurons even, that are tuned to one or the other of these. And the big question now becomes, of course, can we interpret this now in the context of the control of this entire behavior? What does this tell us about how the brain switches between these individual tasks from one to the next, and coordinates them all so that they contribute to running the car around the track? Anyway, let me end it here, maybe with a brief advertisement of my book. If you're interested in the general mathematical methods that are useful not only in neuroscience, but in general in life sciences, we finally published this book together with my co-authors. I can highly recommend it. And thanks to the current and the recent graduates from the Factor. Thank you.
With the daily time, one question is back to it much too early, and then we're charging one. And today we talked about kind of global modes rather than single neural.
Right. So hi everyone. Yeah, it's my pleasure being here. So today I'm going to provide some factor-centric view of cognitive computation. So before factor-centric view, so I guess everyone knows this dominant neurocentric view. When we talk about neurocentric, it means that we start investigating this property of single neurons, right? For like in navigation, there's place cell, bridge cell. If you understand very well, we hope you can understand how animals are given from navigation. Also, for example, in high cognition area, like for decision making, right? People found like neurons accumulate evidence, like single neuron, right a left choice, separate neuron or in memory. There's a neuron to tune. Neurons like in memory, they tune a specific location, right? So everything seems very clear, right? So neuron, you know exactly what this neuron doing, right? But the reality is that single neurons are very complex, right? Especially like in profound context, right? You know that they show very complex patterns, right? People call some mixed selectivity, right? Later I'll show you some examples of mixed selectivity to give you some more intuitive meaning, what exactly that mean. So we don't know exactly how this kind of how to understand this mixed selectivity and how these mixed neurons together to solve this kind of tasks. Right? So today I'm going to introduce an alternative to the neurocentric view and associated not just a view, but also a modeling language. Okay, so I'll start. This is my basic outline. So I'll just talk about use two examples to show single mixed selectivity. Then the means the challenge in neurocentric view, I will introduce alternative factor-centric view. Then I will introduce the factor-centric modeling language. Some basics. In the next lecture, I'm going to introduce more about our new modeling method. This is factor-centric view modeling language. So, okay, I gave two simple examples. One is from decision making, one from working memory. Okay, so for example, people usually, if you have some background, like this neuron, like this is from minus 20 to positive 20. So basically, this is time. This is one single neuron binary rate. And across the time, then this neuron basically at the end of the stimulus presentation, it's monotonic, right? On minus 20, less than minus 20, less than 20 to 20. It's monotonic. This is part of the picture. If you look at a single neuron, almost every neuron is like that. It's understandable, right? This is a strong evidence actually this neuron, if we hold the evidence to show strong binary rate. But in this paper, they found they do some variation of this new task, but they found actually it's reversed. Basically, you can see that this black line basically stands for this weak evidence to show this binary rate. It doesn't make any sense, right? But this is single neuron because since this neuron is not encoding the evidence, right? Okay, this is one example. Okay.
So the difference between the first and second row are
Two different kind of versions. This is the motion version. The sensor features the motion. The second one is the sensory input is a face of it's a face feature. I'll introduce these two examples. And another example is from sequence working memory. Okay, I'll also introduce. Basically, the monkey is required to remember a sequence of memory. Let's say the sequence length 3. So we can say, okay, how this neuron encoded this different kind of audio information. What you can see, for this is neuron standard. Basically, it means a different rack. This 1, 2, 3, 4, 5. This is a feature dimension. The different color, different line in different audio kind of information. Okay. You can see this neuron is more like the game model. This neuron basically shows the same preference for different audio racks. But for this neuron, it doesn't make any sense. It means that, for example, for this blue line, okay, for the first item, to select it prefer item 6, but during the second representation of the stimuli, it starts to shift the preference. So it means that this is making no sense. It's seemingly. Okay, how to understand this kind of thing? Okay, see, I introduce a more detailed way about what this task are. So the first one is this is a very standard classical random dot motion task. Basically, the subject here, the monkeys, presented. They first fix it, and the target will show in the middle of the fixed point. Basically, the feature is basically the random dot motion. So, for example, if the 100% people call stimulus strength, basically all the dots move right, move left. For -10, 100, all the dots move right, and in the middle that's just two dimension of this dot. The monkey are basically required to determine the majority of this moving dots. Okay. So basically, of course, monkey can do the task pretty well. For example, let's say for stimulus strength, for example, it's like larger than 50% coherence, almost this is 100%. If going to stimulus strength from 0, basically it's transferable. Means the monkey can do the task pretty well. Okay. And then after the monkey train monkey do the task, then the experimentals they can record the neuron, right? So basically, this is one task. Okay. And in this paper, we introduced another task. Basically, it's more like the monkey basically required to recognize whether it's a human face or it's a monkey face. Then basically they morph the face, and the monkey the same thing. The monkey required to determine whether it's more like monkey or more human. Okay, this is the same. Similar kind of task structure. Okay, of course, basically people just successfully train the monkey to do this kind of task. Okay. Then basically the polynomial data. This is exactly I showed earlier, right? So basically, they found the motion task is this single neuron. This is private cortex AIP neuron. Okay, we found this is not canonical for motion task, but for face task, do it first, right? How to understand this. And of course, you can basically, if you recall, like say 100 neuron, you can simple average. The simple average, the same similar as this is single neurons. Okay, you can see this is a monotonic one from positive to negative, so this is reversed. But basically, it's not just we found several neurons. It's more like if we're doing average, this is predominating pattern. So the question is, so basically what I'm trying to conclude is that simple investigation, simple response may not be the proper way towards Einstein combination. Okay, this is the first example. Okay. The second example is that, as I already mentioned to you, this is monkey are presented basically a sequence of spatial locations. Here, I feel like 1, 5, 4, right? And the monkey required to remember this and then reproduce this sequence. Okay. Of course, monkey can be successfully trained to perform this task. And then, like my collaborators use the kinds of imaging to record, to neural activity from prefrontal cortex, and then basically we can identify different neurons from this kind of this kind of area, okay? And I'm going to show you it's basically a single video. Then you have this is a bar. I see. I think this is just a very simple kind of video to show, the amount of people performing the task in the neuron, because basically they are fired. That's basically, I'm trying to show this is a data on analyze.
The task was the one thing I have to remember some sequence,
Right,
and
and
reproduce it.
Yeah, right, reproduce it. And then we're going to analyze, to ask what kind of how this kind of sequence memory is kind of represented among these prefrontal cortex.
And this is the recording when you see the
Yeah.
sequence, or you
Yeah, you can see this is it's the whole process.
right, but that's when it's part of the observing the sequence.
Right. Oh, no, this is just look at the sequence, see the look at the sequence, remember the sequence. We are not, in this lecture, I'm not going to present you how they kind of, how they basically retrieve the memory, what's the neural kind of dynamic there, but we have the results.
Question, please. Does the item fragmentation interval impact on the result of the experiment?
Actually not, we vary a little bit, like we will have some variation, okay, maybe I can show you. I think this maybe this equation related to whether it's just time or it's more like right? There's some variations here. But what we are going to analyze is just during this delay period. Basically, the model has already successfully memorized this sequence. So basically, okay, we're going to focus on delay here. Okay, so the delay what kind of information we are interested in? Basically, very simple, right? So there's 6 locations basically called items. There are serial numbers, right? The basic sequence that if you compose, for example, this is sequence with 1, 5, 4, right? Basically, it can be divided like the first rank is 1, the second rank is 5, third rank is 4, right? Basically, this is 3 times 6, there are 18 kind of information, kind of combinations where you should see. Then we are asked, data neuron, right? Because this is a calcium imaging, basically we ignore the dynamics, we just do from the average kind of activity during this period. Okay. Then we ask the activity, how this neuron encoded this 18 informations, right? We just do simple regression. So basically, we will have 18 points, and then we divide it into 3 processes. This is the figure I'll probably show you. Basically, this expected. Basically, it means that the rank information will modulate the encoding and not change the selectivity. But we also have many neurons show this kind of pattern. Basically, they change the selectivity during the presentation period. Okay. So basically, this is what we're trying to again. We try to reconfirm, re-emphasize just a simple investigate single neuron. Maybe not the right way to understand the cognition. Okay, so basically again, I'm going to summarize this. It's a mixed activity. This is a mixed activity. Will challenge this neurocentric view. Okay. Okay, I think like people like as you know that definitely we can simply not just look at single neurons, right? We can just do PCA, right? Very simple, right? I mean, for example, for this case, we can just let's collect like 100 neurons, right? We're not just looking at one neuron, we look at PCA, right? At each point, you can see, oh, from there's no reputation, start to show this kind of, in this state space, you can show this kind of profile, right? And for face class, it's the same thing, right? I think the interesting thing is that if you do that, you see this kind of curve. Then to explain the kind of the average behavior, which I'm showing you this average behavior, this monotonic is the non-monotonic, right? So basically, it's related to this basically how this kind of how curve man, how it's a relation with this and the average area. This axis is just 1, 1, 1, 1, 1. Okay, the average axis. So basically, it's monotonic means that if we project this neuroactivity to this percent, this axis is just monotonically projected. For example, this one, the largest, that's consistent with this picture, right? But if we look at this, basically, you can see, okay, and at this point, basically have the largest projection in this axis, right? It's very intuitive, right? Basically, and then people can, okay, so this is now my collaborator, they say, okay, you can look deeper. Basically, they can define, actually, this curve manifold on this direction, it's monotonically, with respect to the input. So, right, it's called a decision variable. It's more like a decision, right? But for this axis, it's more like difficult variable. It's the absolute value of the input. Okay, so basically, what is the explanation is that, okay, we can introduce additional stimulus difficult variable that which can explain this continuity primary reversal. Okay, this sounds good explanation, right? Okay. For example, sequence multi-memory tasks, make the same thing, right? Instead of asking how this sequence information is encoded by individual neuron, we ask how this variable encoded by the neural population, right? Then we can introduce, we're not looking at one neuron, we're looking at many neurons, right? This is called state space. We ask how this kind of 18 kind of combinations encoding in this space, right? This is one we expect to make sure to go like this, right? The first is basically the first rank information is critical to look like this, right? Maybe it should like this, what I expected, right? This is what we are expecting. This is what the real result. The real result is not very. It's kind of consistent with this picture, right? We can do, find one subspace equal the rank 1 information, the second subspace equal the rank 2 information, so rank 3 information. Then the question is that because this is really high space, right? Then we can just quantify the geometric relationship between them, right? For example, we can ask what's the angle between this subspace. Basically, what we can find basically then you are solvable. Okay. So basically this is a simple way just doing PCA, right? You can see okay which is expected, which is consistent with our expectation, right? So basically different kind of sensory input in different ordinal ranks should be presented by different subspaces. Right? If you can also there's good property, right? If encoded by orthogonal subspace, then you can just simply linear read out this kind of information for further processes. For example, for the retrieval process, right?
Why not separate the ranks? If we have done PCA on the vector, right?
Of course. This is because this is hypothesis driven, right? We just look at okay whether this is the first stimuli, whether the shape, the form of the shape, the ring, right? And then we ask what this kind of space geometrical relationship is that. Also, actually, we did a lot to verify this behavior relevance. Okay, for example, if let's say these two are switched, if we look at activity switched, if the behavior will switch, actually found this kind of evidence to support this is not just kind of if a view is. I think this is the behavior relevant these subspaces. All right, right. Because you have a sequence, right? Oh, that's the question. The rank here is the first, the second, third, the rank meaning. So this sequence is not just like sequence. There's the ordinal rank is the basic element of sequence. The first of second, third, right? Because basically this is the one way, I think one simple way to compose this. Okay.
In the data that we see the rank 1, rank 2, rank 3 ring, they have showing the neuron data as a photo of times because you show the first.
I will show you actually later. Okay. Definitely you have.
So a question about the subspace orthogonality. I mean, if the neurons are randomly distributed, this would be naturally what we would expect, right? Because we are in a high-dimensional space.
Right. I think that's why that's exactly why our brain uses this kind of phenomenon, this structure, right? It's very easy for these kind of subsets to be orthogonal. Then there's no interference, right? I think that's exactly that's a good property of high dimensional space, right? Okay.
So then maybe this explains Markus' questions.
Okay, I think that's a good question. I'm trying to refer to that. Okay, it's good, right? I think why we need that high dimension because our brain, really, our internal brain, need to represent lots of things. Of course, we need something else, right? In the high dimension space, right? Okay. So basically, we can also understand how this kind of similar property happens. Because if you have this high dimensional space representation, then if the neuron basically transfers one axis, right? The geometric relationship between this axis with respect to this different subspace determine, whether it's this kind of real shape once again available, right? I think it's pretty easy. Okay. So basically, I'll conclude that basically now we have a two-level kind of view of computation, right? Basically, if I look at single neuron, it's super complex. Even sometimes it makes no sense, right? But look at collective level, it's super clear, right? It's very simple, right? For example, here we can different variable, we have deleted variable. Here we can just have different kind of subspace, different kind of ordinary information. Okay, so the answer is fine. Okay, seems good, everything's good, right? We can explain everything, but is that explanation? I would say maybe not. Then we can, when we look at, if you record neurons, we're going to, for experimental instance, you record neurons, you actually do this kind of analysis. Okay? Seems very simple, like PCA, right? There's no tricky things, okay?
Suppose I were thinking that I'm including the following. I remember the rank 1 number.
Yeah.
And then I remember the difference between rank 1 and rank 2. There's a difference between rank 2 and rank 3. And I did PCA on those differences. I would also get some image like this.
No.
But the two inclusions have very different implications for the error.
Right, definitely. I think it's a very good question. So first, the data is not like that. Basically, you're saying is using relative right? Yeah, but I was arguing that's not the name. Definitely, the data is not like. We also basically you have another kind of hypothesis we can analyze based on that kind of hypothesis. We analyze data. See, data is not like that. Okay. So first, also this is because this is also relevant. I think for these experiments, because we design experiments like not use this kind of relative kind of structure. We basically make the first line, second and third line. Basically, the relationship. There's no clear kind of relationship. There's no clear structure. Basically, the first item, the second and third item, they're independent. This is it. Due to the experimental design.
There are many examples where the current to be found independent, yet the encoding is not.
But we can talk this later, but it seems like this. Okay. So also we can expand data. Okay. Or we have dynamic version.
Use the more factor. It seems to me you say if you cannot expectations. What do you mean by factor?
Factor means basically the factor. Basically, this is you can say this is more like we give the meaning to this kind of dimension, right? So for example, in this dimension, if we project it, basically it looks like in code the decision variable. We call the variable basically equivalent to factor, right? The decision variable factor. Okay. But it is the same, has the variable factor. Yeah, exactly. Here I just maybe I should, sorry, I just I need to use this kind of terminology. Yeah. We call it factor. Yeah. That's a good question also. If you go to train on end, since there's some inductive bias. Okay, so but what's exactly the reason why it looks like that? I think we clearly right now we don't have very clear understanding. For example, for human, people also see the primacy effect and the resistance effect. But for this monkey, there is no. But for why it's looking like that, we don't have very good. I don't have a very good understanding. Yeah. Maybe it's related to the task structure, related to how we contribute this kind of task. But it depends on many kind of facts. Okay. Okay. Then so this is here this is dynamics. So basically this is our another paper. Basically we can we were using electric physiology, not just a two-photon imaging. Is too slow. This is electric physiology part. We cannot the data. We actually basically we can visualize this kind of dynamics. Basically, I think this is also very important. Basically, it tells that actually when the first comes, it directly go to the first subspace. When the second comes, it directly go to the second. Right? So I think it also means there's some control, right? Some gating. The gating process gives you some kind of hint, right? For example, for this kind of example, you can also visualize this kind of how this kind of predict form through dynamics. But I will call this is basically this is dynamic visualization. It's a certain visualization, right? They don't tell you, right? How this kind of representation form, right? Okay, just to come to there's no mechanism understanding. Okay. So here because we are conditional side, we really when not use data analysis, right? Living model. Here to answer this question, I'm arguing basically to request no living model. Okay.
So these are like the representation after the animal consumption.
After learning, exactly. That is not the learning itself. Yeah. Okay. Basically, as I said, it's a representation. We have the representation, but we don't know how this will perform. When I say form, it's not how to learn. Basically, it's in a trial how this kind of dynamics, how this kind of basically information flow basically control. Maybe I need that's technical question. I'm not only going to ask the learning problem. I'm going to ask the information flow control problem. So okay. So basically, I hope I give you a sense like why when we really need model. Okay. Or before that, until now there's no new model. Okay. We just do signal analysis. Okay. So basically, okay, look at modeling. Basically, I would say, okay, this field is dominated by the neural signal. Okay. For example, in the field, this basically, okay, select one neuron. Okay, you have one neuron pool, the second neuron pool, they compete. There's recurrence in one pool, in each, they compete with each other, and there's input coming, they compete each other, and it's decided okay, left or right. Okay, there are basically there's a couple of parameters. Okay, basically return, inhibition, and microstrain, right? Okay, it's handcraft. We can manually kind of build the model. Okay, with the exact equation. Okay, then of course we can create a variable. Okay, we can plot out this kind of attractor, right? The vector flow, everything. Okay, because 2 dimensions. Okay, okay, this is pretty good. Okay, very possible. Okay. Also in this field, in these days, people are starting to using RMs, right? To model tasks and more complex tasks. Okay, and of course, definitely now this is in the other extreme. Now if we have say have n neurons, how many parameters do we have? We have n squared, right? And lots of parameters, right? And how to learn? It's not handcraft. It's learned through aggregation, right? But people know, like IP, right? Because the IP from already. This model is black box, right? We know that how it works because it's almost impossible for us to understand. Okay. With n squared, right? If n is 1,000, right? It's 1 million parameter models. How can you understand one model with 1 million parameters, right? Okay. This is basically the dominant kind of modeling framework in the field. Okay. Then what factor-centric modeling should look like? Let's say just say we are this simple discrimination. Okay. I guess the people, I guess we should like we should like this, right? It's a factor-centric view, right? You should know this is not instead of neuron, it should be factors. But who did make it? You have variable. Did you variable? It should be like that, right? And there's some connection. When you put it like this, it's a variable. You integrate the input. Okay, this is sort of the picture should be like that. Okay, then what is the mathematical language for describe the system? Okay, they want we think can of course we should emphasize the if we don't emphasize the value this we should be satisfied with this kind of model. Okay. Okay, okay, how the number of parameters scale the task complexity, right? So definitely if tasks become more complex, we definitely need more parameters, more complex models, right? But what's the relationship between them? Okay. Then of course we don't want to manually or handcraft model, right? We want to learn through replication. Okay, and learn. Okay. Okay, this is basically this is all the conditions basically we want to fulfill for the new model. Factor basically a factor for the decision variable. So like raw memory is a factor, input is a factor. So basically, for example, language, each word is a factor. Okay, this is called factor. Instead of neurons, we're interested in using factors, the names. Okay. Okay. Maybe I continue. Okay, more questions? So basically, towards this kind of language, I'm going to say I've divided into 3 parts. This is the work from lots of people, right? Especially like Zhou here, right? He involves searching of storage, right? Basically, not his lab, there are lots of different kind of labs, right? Like hands-on thing, right? The people they do this kind of I would say this is a very fundamental kind of modeling kind of work which you do. So first I'm going to say okay, because this is still it's an RNN, but we need to restrict the RNN. We need to make some assumptions, especially regarding the connectivity structure. Okay, there's 2 major assumptions here. The first assumption is lower. What do we mean by lower? So basically, giving I give you negative behavior here, it's very complex. Okay. The basic low rank means basically it's a very simple single value position here. For example, I divide into these two different collective modes here. If we write like this, okay, basically now complexity, the parameters from n squared to 4 multiplied by n, right? And on 4, right? Okay. And we call this vector called upper vector. This vector called input selection vector. I will explain what it is meaning of this vector. So why we call this upper vector is called input selection vector. Okay. And also I want to mention that this output vector, they are mutually orthogonal. This input vector, they are mutually orthogonal. I also want to comment this vector and this vector, they could be totally different. If they are same, they are symmetric, right? They're symmetric. It's possible. They're symmetric possible. But in general, it could be very different. Okay. Okay. Then the children meaning of input selection output performance. I will just use very simple math here. Let's say we have this is basically linear transformation, right? Let's say have a input. This is called factor. Okay. I have a factor which is embedded in I input. This is another connectivity. Basically, you can think about this is just a word I can embed into neural network. Okay. Then I'm going to basically transform this kind of information through this linear transformation. And the W is just these two low rank form matrices, right? Multiply by that. And then it just looks like that basically this part basically the inner product, right? The input. Is it clear? Something is wrong here because it's converted to PPA. So sorry for that. So basically this is just an input. This is an input. Okay. So you can see it basically converts this initially this kappa input this vector is living in I input. Then but after this transformation, we have two components. One is N1, the second N2. Okay, we call it. So that's why basically output vector N basically output direction of the new transformation. And the input selection vector basically plays the role that basically it is the inner product between the input embedding and this input vector, right? It's basically going to select one here. Let's say if this I input and they are orthogonal, it means that it can't be arrived at anyone because it will go to zero, right? So basically, I think this is very important structure here. Basically, this is a selection process. Select what kind of information can be further transformed to the other space. And right.
I cannot always rewrite matrix with orthogonal vectors, right?
This is selection. This is single value dependent. In principle, any matrices can be decomposed by this kind of form. But in low rank means basically if for any matrix you write like n, there are n modes, right? But low rank means there are only few. Like here, I just gave two.
Which is, if I have, say, around 2 motions of Johann, can I always write it with chance and ends and orthogonal or
you can, of course, right, you can do, but not like this. You can, in there you can do, for this matrix, I think here, to answer that, your question is the way I can do basic organization, right? We give you two, I can do the optimization. But here I'm trying to say for any matrix, you can use decomposition. But when I say low rank, means there only a few. It's not like n, like 1, 2, 3, 4. This is a strong assumption.
No, that's part.
Okay. But you say, okay, for it's not orthogonal, can be orthogonal related, like a Schmidt kind of organization there. I think this is just a beginner. Okay. So basically, I think this kind of picture means that it's also very it's also very close to like for decision making. Basically, they say that the kappa image can go through just rank 1. It can go through this kind of linear transform, and then it will be living in M1. This computation. Okay. It's already very close, but without this kind of this is just linear part. Okay, this is I will emphasize this is a very important kind of structure. Okay, this can be in product. Okay, this is one thing. Okay, I will continue. Okay.
All those background here is component with each other.
I mean, these are orthogonal. That's and orthogonal to M2. There's no there's no relation. Two orthogonal. Overlap. One is overlap. One is the same. It's obvious, right? It's symmetric, right?
So kappa here is a scalar, right?
It's a scalar. It's a scalar. It's a scalar basically embedded to the input. This is another connectivity, right?
For generalized form of fields.
Yeah, exactly.
Each are always interlinear.
Yeah. The people also in the field call it also if the n is the same for normal matrix. Also people call it non-normal dynamics. And actually it's also related to Markus also present a figure from Manchester's work, Nature paper. Actually they in that work which I also talk about that kind of work. Basically that's they use this non-normal kind of matrix to understand what the dynamics. Okay.
But you should construct connectivity matrix.
So this is assumption. So basically, if you get any, you mean biological, right? So I think it's an approximation. It's an approximation. So basically, if you any kind of connectivity, always can be composed in terms of this form, but it may have n kind of this kind of different modes. But here we only assume there are two. But I don't have the anatomical data to support that, but there's a lot of actually like this kind of data analysis with that actually you can it's pretty low rank. But there I would say different fields have different kind of view on different kind of view. For example, if you want like people say okay if you want there's many dimensions. But I would say for example in the high cognition people usually find since there's you only use a few modes already explained, at least the electrophysiology. Okay. How much time do we have?
We're at the top side.
Okay, good. Okay, this is limited. I think it would be maybe I'll teach you now. Okay.
Let's take
So okay, this is the first assumption. It's basically low rank. I will try to say low rank. This low rank is not like non-normal. It's non-normal. Okay. Basically, it can transform one information in one subspace. For example, from in one subspace to the other one. I think that's basically the mathematical structure I want to emphasize here. The second example is that, for example, in the last two examples, if you say, okay, look at this state space and description, right? Okay, but actually, I do not stick to cell types. There's no notion of cell types. But we know cell types offer constant. It's the most important concept in neuroscience, right? Definitely we cannot miss that. Okay. So then, how do we introduce this concept? for example, model. Okay. Here, okay, we already assume, okay, it's like low rank, but there's no cell types. Okay. I think that the idea, like surgeon or storage, they propose is that, okay, we can introduce this kind of structure. Basically, okay, we can introduce, for example, there are four, for example, rank 2, right? This is N, N1, N2, N2, but basically there's 4 directions. So basically it's a 4-dimensional loading space. Okay. The idea is that basically we can define cell types through identifying clustering structure in this loading space. Basically, okay, you can just look at, let's say there are 4 different dimensions, like one is M1, M2, N2, right? Okay. Okay, let's say instead of look at like column wise, you can look at each row, okay? So let's say, okay, this is 4 values, right? And for this is 1 neuron, okay? 1 neuron connected value, and 1, and the neuron 1, it's a neuron 1 and 1, neuron 1 and 2, right? And 1, and 2, and 2. So basically, it's a point in this space, okay? So because we have lots of neurons, right? So if lots of neurons, look at this. You can say, okay, this is more towards the 1 class. So basically, okay, this is 1 neurons, 1 type of neurons. But also, of course, we can have this kind of space. Okay, basically, okay, so we have 2. Okay, basically, this is definition of cell types here. Okay, okay. I would talk about this. Why this kind of cell type? How this kind of cell type? Why cell types important for neurocomputation in the next lecture? But here we just introduce this kind of concept. Okay. So also, I want to emphasize, by introduce this kind of concept, basically now the parameter is from, at the beginning, it's an n squared, but now we have, let's say, we have m class or n modules. And for each module, because we can simply, let's say, the clusters, for each cluster, basically we can use a Gaussian, right? For Gaussian, let's say, there's a mean and covariance structure. And the Gaussian, the dimension is R, right? So it's R squared prime, right? So basically, with that, we have a really, I think it's important. Basically, we reduce from n prime number from n squared to n multiplied R squared. And in the next, also in the next lecture, I'll emphasize since it's a kind of optimal, the least number to we can define how many modules do we need for task, and how many ranks do we need for task, and then we can define this may be the optimal. So basically, that will another kind of measure to define how complex the task is. But in this lecture, I'll just introduce this kind of concept. Okay. So okay, basically there are 2 structures, right? There's one low rank, and based on this low rank loading space, you can define different clusters. Okay. So basically, we have a statistic kind of description for the connectivity. Also, want to emphasize this is more like general for connectivity, right? All we need is how many clusters we have, and the covariance structure for each clusters. Okay. And the total number is just n multiplied by R squared. Okay. But the neuron, we can sum as many neurons you need. Okay, because general model. Okay. So okay, let's say we have this kind of we have this kind of structure. Then how we can from this connectivity basis structure to dynamics and computation to function. Okay. So let's go through this. I think this is just assume people have some kind of ordinary differential equation background. But I think it's very, very intuitive. Okay. Basically, let's say we have rank 1 RNN. Basically, this is a hidden variable, right? This is x itself. They will decay, and the receive this rank 1, right? This rank 1 matrix receive the input for all the other neurons and also receive the input, let's say the kappa input, and embed in through I input. Okay, this is a very simple kind of RNN. Okay, and if you have this kind of form, basically you have to make an answer. Say this hidden variable, it has to be the combination of these two terms, n multiplied by this kappa t is a scale, n is a vector. Okay, and I input, this is also new input sheet is a scale. Okay. Also, actually, you can look and see why x should be like that, because x equals less than b0 has to be linear. It's a linear kind of combination. The n and I, right? So basically, there's some assumption. Okay, if we have this assumption, we can look at this is the linear. Only complex thing in this model, it is non-linear, right? Because it's non-linear. Okay, you can insert there. And okay, let's just look at the picture. The picture is just like x like that, right? And this is x. Okay, let's go to phi, and phi is a non-linear function, and multiply nt and n. Okay, still here the key thing is that this part, it could be very complex. If there's no nonlinear here, as I mentioned earlier, it's very simple, right? This just inner product of is nt, this input selection vector, multiplied and embedded. Okay, inner product, the super easy. If there's phi, it's nonlinear. Because if phi is applied to each neurons, it could be very, very complex. And then people also, there's a universal approximation. Basically, if you have enough complexity, basically it can approximate kind of dynamics. So it means it could be as complex as you want. It could be very complex. But here, if we make an assumption about these connectivities, then we can simplify this kind of complex computation through using, for example, in physics, it's called mean field theory. In mathematics, people call Stan's lemma. Basically, it's like this. So if just take a look at this and multiply this, the sigma n basically just an inner product of this. First, I want to emphasize, right now we decompose the two, because there are two classes. Okay, the red one and this blue one. Just focus on the red one. The red one for nt multiply this is it could be so like this is just the connectivity, the inner part. I think the key thing here is that it will be kind of multiplied by this nonlinear, the derivative of this nonlinear activity function, and average across all these neurons. Okay, and for second, this blue one, same, is equals to the inner product of this n multiply the n. Okay, and then multiply the second cluster, the second module, that's average derivative. Okay, and then this is for this kappa. Look at this. This is kappa t. Kappa t basically it's a cost variable, or it's a factor lived in n. Okay, so basically it's more like kappa t, and then this action basically quantify how strong kappa t will affect can send to this space. Basically, it quantifies the effective connectivity from kappa t to kappa t. This is recurrent, right? I want to emphasize why it's called effective connectivity. Basically, if there's no nonlinearity, basically this is just the connectivity, right? There's no activity dependence, but just fine. This is an activity dependent, or it's state dependent. Okay. Okay. This is basically kappa t. For this term, it's basically it's a new input kappa t, And then it pretty much looks like this, right? Basically, I have a cut. This look at this, and we look at this part. Corresponding to basically is the new input sent to capacity, and the strength is this part. We call it effective connectivity, right? And this part equivalent to, right, the capacity. This is recurrent, right? This is exactly what we really like, right? And the difference from neurocentric. For neurocentric, we have different neurons, and neurons, just connectivity is fixed, right? But here, this effect connectivity is state dependent. Take over all these neurons. This is because this is a red one is operation one or called module one. Okay. Okay. And this we can it's self-consistent. It can depend on all the state. Okay. Okay. I will say, okay, we already have, okay, what we want. We have mathematical language to describe this factor-centric kind of interaction, right? The factor, for example, can sustain by itself. There's a recurrent connection, like just input level. There's window connectivity, right? We have it. And I only say with this rank one, but we have this kind of language can deal with many ranks. Also, it can deal with many populations, depending on how difficult, how complex the task is. Right? Okay. So once we have, now this is very abstract, and then I'll give you a simple example. So basically, this is a recent work. Use this kind of language to address the selection mechanism in context. Okay. So basically, okay, this is actually Markus also mentioned the context-dependent decision-making task by Zhou from Stanford. Okay, basically this task is a little bit more complicated than what I mentioned earlier about the decision-making. Here, basically, there's context. For example, there's the context. Also, there's the feature is two-dimensional. One feature is color, blue or red. Okay. Green or red. Another feature is left or right. Okay. So the basic features are two dimensions. There's also two contexts. In the motion context, it means the subject here, the monkey, has to make a decision based on the motion evidence. But for the color context, the subject has to make a decision based on the color evidence. Okay, this is a monkey version. Actually, this year, from Chaos Studio Lab at Princeton, they also have this is a rat version. Basically, the structure is the same. Here, the only difference is that the subject is different. This is rat. Okay. Also, the feature is that the left or right, or high frequency or low frequency. The right has to make decision based on context. If the location context, the right has to make decision based on left or right. For right, basically compare left and right place. If in the focus location, the right has to make decision based on the frequency. Whether they are more high frequency parts or they are more low frequency parts. Okay, but look at this. If we do model the same, okay, there's two contexts, two features, and based on the rule make a decision. And in this kind of work, they raise actually a very important question: is that what kind of mechanism underlying this kind of context decision making? They propose at least there's two kind of mechanisms. One mechanism is that, let's say, there's a frequency, this is a state space description, okay. There's a frequency, there's location. Actually, they propose there's another concept they call selection vector. What selection vector doing is that basically only the information aligned with this direction will be selected by downstream decision making kind of process. Okay. For example, in a location context, only location basically align with selected vector. So a location information will be selected for the downstream process. But look at frequencies orthogonal selected vector. The frequency will be ignored, totally ignored. Okay. And then in frequency context, only frequency will be aligned with selection. The location is orthogonal. Compared to these two cases, you can see selected vector doesn't change, right? The only change is the sensory and location. Sensory kind of direction, right? This switch. Okay. So this is called input modulation because only input is modulated. The selection itself, selected vector itself is not modulated. Okay. And the alternative is that this kind of sensory kind of input is not often changed, but only selection vector is changed. It's called selection vector modulation. Okay. And what they found actually, there are two different mechanisms. But if you're doing the same kind of analysis as the Meister did in their Nature paper, actually they show similar kind of profile. So basically, there are two different mechanisms, but this have a similar tri-average thermodynamics. Okay. Is it clear? So basically, basically say that, for example, the Nature paper, the Meister work, basically, if they basically they found this kind of dynamics, basically they can't decide whether this is, they can differentiate whether it's this input modulation or selective vector modulation. Okay, then basically this is calling for receiving what kind of evidence that require to differentiate different selection mechanisms. Okay, this is a little bit complicated, but I'm trying to say this is a basic picture.
In the context variable presented after
and it's presented before. It's in the default password. During the fixation password period already is there.
lucky node.
Okay. Yes.
Other experiments have been done where that
They're different kind of versions. They're different.
that allows you to tell the difference.
Right. That's a good point. But I don't know why these guys didn't do that. But I think here, actually, I want to make a point here because, as I said, I already introduced this selection vector. But what is selection vector? It's prediction. And what our work basically in the econ, basically we're going to use this kind of the language I mentioned earlier to address this question, especially to elucidate what is selective vector. Okay, then to do that, basically we know the language very well. Okay, basically we can construct the connected pattern. Okay, this is a little bit complicated, but let me explain it to you here. Basically, there's two different pathways here. One pathway is basically this input. It will be directly selected by decision variable. So the N is called selection. Input selection, right? This is selected by the decision variable, then it directly go to the decision variable. But in this model, we also introduce maybe there's a second order pathway. It means that the input not directly go to the decision variable. If it goes first to another, we call it intermediate variable. And the intermediate variable, they go to the decision variable. Then it's more like this. So basically, the input, this is like first order kind of pathway. The input gets directly go to the decision variable. But there's another second order pathway. You have to go to first to intermediate variable, then go to the decision variable. Okay. And then here E stands for the effective connectivity. Notice that I also want to mention that these are all state dependent. Okay, this is not fixed. Depend on different areas, different context, depending on the decision variable. Okay. So now we are going to this very simple algebra. Okay. So basically, if this can be, we will say, okay, this can be reduced. I think the same motif comes. Basically, this is the inner product. The inner product is just a scalar, right? So basically, we can denote the. So it's more like, okay, we need to go to another step, but effectively it's multiplied by this scale. Okay, basically it's more like, okay, there's a multiplication from this effective connection multiplied with another effective connection. And then we can further replace that. So basically, there are two paths there, and we can add them together. Note that this everything is rigorous, not like just a point. We can add this together. Okay. So then, after this kind of operation, then you can immediately see, basically, we can explicitly write out water selection. Before that, people they don't know water selection. Back then, they can have very complex, very complex numerical algorithm to compute selection vector. But this is the first time you can write out what is selection vector. Basically, selection vector is basically selecting. Basically, as we said earlier, it's input selection, right? So basically, to determine this input whether the inner product is definition 2. Okay, we can see, okay, if without this second part, the NDV itself is not context dependent. Only this term is context dependent. It means what? It means that we really need an extra dimension to have selection modeling, because this is the NDV itself is connectivity. It's not context dependent. It's not state dependent. Only when you have a second order selection pathway, you can have selection vector modulation. Okay. Then basically now we have a basic new geometrical understanding of the selection vector modulation. Basically, maybe it's a little bit complex, but the key thing is the same. So basically, you need extra dimension to have selection vector modulation. Okay. So we can say, okay, we can generalize actually not like this toy example. Actually generalize the more complex stuff. This kind of graph. Like you can tell for this kind of graph what is selection vector modulation, what is input modulation, and then we can validate in like foreign column without strong assumptions. Basically, we can compute. Basically, our kind of prediction is that the more dimension you have, the more selection vector modulation you will have. Okay. Then we also provide this kind of index that you computed from your experiment, from data experiments. Right now we are kind of analyzing real data. So basically, I would like to conclude. Basically, this example is showing you that if we have this kind of language, we can do some interesting thing to elucidate some like very, very kind of complex concept. For example, selection vector in this field. Okay. So, okay, let me conclude here. Basically, I want to emphasize here, in this lecture here, basically, to say, okay, since we have I think it's better to have a factor-centric view to really kind of accommodate both the single level complexity and the collective level simplicity. And because this is just a view, and with this kind of view, now we have associated model language. Basically, it's link, connectivity, and dynamics and function. And I also want to emphasize, right now, there's lots of remaining issues. Right now, we don't know how the number of parameters scale with task complexity. And we don't know, right now the model is just handcraft. It's not learned through aggregation, right? And the more important thing is that today I introduced these two examples. Right now, these two examples remain unsolved. In the next lecture, I will introduce a training kind of framework which can train through aggregation, which also we know how model parameter scale with task complexity. Also, the model has a very good dependability, and we also will resolve these two problems and make a prediction and then get a verification from experiment data. Okay, that's it. Thank you. That's a good question. So I so basically, it means the single neuron also may also include a non-variable like this. Yeah. Of course, this would be nonlinear. Yeah. Yeah. So remember this double edge arrow between them represent a lot of neurons. So so each neuron here it can represent only, for example, input, or only represent DV, or only represent IV. But in our model, one neuron can also include simultaneously include all three vectors. Yeah, exactly. It could be allowed in any kind of combination of complexity. Yeah. I think right now it's depend on. I think right now for this kind of task, it really depends on how we design. We can use the less selective neuron. We can also use more selective neuron. But right now there's I don't have very clear kind of it depend on. Maybe I want to emphasize. So basically, our model have the ability. If you give me the data, I can fit that. It's very expressive. Yeah, but in general, yes, yeah. Right now, yeah, it's not well constrained.
I don't want to clarify one thing. So currently for the model, so your output, like, are you only trying to simulate the mean output of the neuron, or consider covariance between different neurons? Because I'm just thinking, like, if you assume that if it's low rank, let's find some covariance figures.
The neuron are covariant, definitely. For example, these neurons, the connectivity are covariant. Of course, activity has to present some covariance.
I mean, I will check whether that if the different population the covariance figures derived from different models, but that fit with what people observe.
The noise formation type of stuff. We haven't. Definitely, we need input from experimenters with simultaneous calling data, like you. Yeah, definitely. I think that's a feature kind of really, I think, very important exploration directions.
So as you said, the model is very constrained. So what would be the experimental chair?
Okay. So next, depend on. Actually, in the next lectures, I'm showing you actually this kind of logical structure actually present in the data. You can make a very specific kind of predictions, and you can verify experiments. In the next lecture. Also, we have different kind of learning. Right now, our model is definitely it's hand. Today's part is just hand part, just built by hand, right? The next lecture is more like IM, like it's not data driven, right? You have input output. If I want to have this input output to solve the task, we can train a model, make a prediction, and do verification. Also, we are developing a more data driven approach that could be more better than fit.
So this mean field theory, that does their results depends strongly on this mean field assumption? I mean,
yeah. So when I say I want to have a model with high interpretability, it means here I have a model basically have mean field. Basically, it means when I say model have interpretability, it means have mean field limit. Right. Also, I think in the next lecture, even I have a model, I will train a model, but still, at each epoch of training, the mean field kind of limit still holds. So basically, it's more like I'm not training black box model when I train white box model. When in white box means have mean field limit. It have a collective level or statistical kind of level kind of description. It's not like million of parameters. It's the parameter, the number of parameters and scale with the complexity of the task.
So what do you mean by mean field here? Because the traditional statistical means that the average over disorder quantities of the calculation of what was the mean by mean field? What average is
the average is basically look at the lot of neurons, right? Then after mean field, it's only depends on the statistic structure of the connectivity.
Or you want to mean you change the level, you don't learn your statistics, you don't learn the explicit pattern.
Yeah, exactly. In the next lecture, I only have my model to learn the statistics parameters. Only learn statistical structure. No. It's kind of multi. It still have a neural network. It's generated from the general model. Depending on which level you are talking about. At this level, yes, only depending on statistical parameters. But we also have this kind of implementation level. Right. Yeah, I will talk about that next time in the next lecture.
Okay.
Hello. That's the introduction, and most of and you have heard a lot of things about population activity, and my talk will tell you how to predict population activity from functional unit data set. My background is I got my bachelor degree in physics and a PhD about machine learning and neural computation. So I mainly care about the efficient method for processing neuroscience data sets. So my interest in neuroscience starts from the key question: how do billions of dynamically interacting neurons produce intelligent behavior? And I care about the two questions. First one is how do neural populations encode and decode the behavior relevant information? The other question is also how do neural circuit architecture physically implement this neural computation? So to answer this question, we need collecting a lot of data sets. So these days, thanks to the advanced neural technology, we have very two techniques to do joint behavior activity recordings using pattern imaging or neural picture recordings. And also we have mesoscale whole brain 3D imaging to reconstruct the structure connectivity
between different regions. So this is a modern neuroscience research paradigm. It's that is in technical lab. So in this project, there are 19 labs involved in this project. There are 11 of them doing experiments, and the other 8 computational labs. So they all these experimental labs collecting data in standardized behavior tasks, decision making, and they collect a lot of data set using electrophysiology to photo microscope or fiber technology. After collecting this large scale data set, 93 terabytes data, they process the data and upload them to the cloud. And the computational labs can analyze this data set and build a computational model to explain the data set. So this modern neuroscience research paradigm is about experiment analysis and theory. So in this cycle, there is a critical part about the analysis. So 15 years ago, when I started doing neuroscience, most of the data that I have seen are recorded using single unit effective recording of 64 multi-electrode array MPA. So usually the data set is only terabytes, gigabytes step. It's a scale of gigabytes. But usually there are a lot of, for example, passive imaging data sets. We can easily be tens of gigabytes, and most labs are collecting passive imaging data set over terabytes. And also for the whole brain structure imaging, the data set can be very close to terabytes. So when we have so many data sets, if we still use the conventional method to process your data, there are a lot of obstacles. At first, you feel the conventional methods are very slow. So this is okay. It gets slow. If you have lots of people, lots of graduate students working on this, then it's okay. But sometimes some programs, the conventional methods are suboptimal. You couldn't get all the information from the raw data set. And for some data sets, when the data at the scale of terabytes or terabytes, it's almost mission impossible. So collecting data is challenging. So we must maximize the value of raw data through proper analysis. So my research direction is about the neural data science. So experimental neuroscientists collect raw data from the brain, and I will develop some signal extraction methods to pre-process the data, the raw data set. The raw data set can be time series, images, videos, and given this process data, we can apply lots of population analysis methods to do data mining, and eventually we will find some scientific discoveries. So today I will use a passive imaging as an example to tell you how neural data science have helped neuroscience research. So for different audience, I have different goals. So first of all, for experimental neuroscientists, it's probably those who are collecting data using passive imaging. I hope them can know the methods for processing passive imaging data. And but most importantly, I want them to be aware of the power of computation in extracting more information from your data. Sometimes you feel the data is very hard to analyze, but you may feel that you couldn't get the data, but actually with proper analysis you can find more information. And for theoretical neuroscientists, I want them to know more about the processed data from your experimental collaborators, and be conscious of the potential flaws or artifacts in the processed data. And for people who are interested in methodology development, I want them to know how to formulate a data analysis program into a computational tractable question in machine learning or statistics. And also I want them to be open to real-world bottlenecks and unmet needs in neuroscience. As we all know, there are two main streams, two main approaches for recording neuron activity. One is electrophysiology, and the other one is the optical approach. And for optical approach, there are calcium imaging, voltage imaging, imaging of some other neurotransmitters. It's an indirect way of measuring neuron activity. The basic idea is when neuron fires back, the intracellular calcium concentration increases, and this increase of calcium concentration will be reported by some fluorescent indicators. So calcium imaging has a lot of advantages. First, you can do a very large population recording. We can easily record 10 to the order of 5 neurons. And we have their precise spatial locations. And also we can do chronic recording. We can record the same population neurons across weeks. And most importantly, we have the cell type selectivity. But it also has some disadvantages. There's a low temporal resolution, low signal to noise ratio. These days, there are lots of advances in imaging techniques for different purposes, for high resolution, and for volumetric imaging, and for freely behaving animals. But these advances in imaging techniques allow us to collect a lot of data. But for analyzing these data sets, there are several computational demands. The first one is back inference. So the recorded neuron activity is like this, is a fluorescent stream, and in most computational model of neuron activity, we are very familiar with the side count. But for fluorescent, for calcium imaging, we have to convert this fluorescent stream to something like a side count. And the other computation demand is that soft extraction, which is the most important demand. So we have to identify all individual neurons first, and then we have to extract the individual neurons activity. So given this activity, we can also apply the stack inference to get the stacking count at each point. And this is motion fraction demand. So because these days most calcium imaging data are collected while the animal is freely behaving. While the animal is freely behaving, the field of view is shifting. It's not stable, and this is usually eroded. And but for the downstream analysis, we have to first make the field of view stabilized. So this is called motion fraction. And also the data set, the raw data set, sometimes it's very noisy. You have very low signal to noise ratio. And if we can enhance the signal to noise ratio like this, then we will get a better signal quality, and most downstream analysis will be much easier. And also, as I mentioned earlier, that we can use passive imaging to do chronic recording across multiple weeks. So when we do multi-session recording, we have to register the same neuron across different sessions, so that we will know the functional property of one neuron in session 1 and its functional property after many days. So this will allow us to start something like memory or learning. So this is the outline of today's lecture. So we will cover all these five computational demands. We will start from the stack inference. The goal is getting a fluorescent trace, import the hidden stack count of stack timing. The most simple approach of doing this is we start from a generative model. This is a broadcasting phase. It's very noisy. And we're going to build a generative model about how this noisy data set was collected. And that is, we want to build a generative model what kind of information is included in this logic observation. So first we will compose this your log treat as a category concentration plus noise. This noise is main about the recording the observation. And this category concentration can be further decomposed into a convolution. This is a convolution. A convolution of a tracking activity and a kernel. This kernel represents how a neuron responded, how the category concentration was increased in response to one spike count. And given this generative model, we can solve an inverse problem. Solving an inverse problem is that we are trying to find a spiking count in a variable s given this observation. And here we assume that h, the response kernel is known, but actually this is this can be roughly estimated with some trick. But we can also optimize h as well. In that case, it's called double-blind deconvolution. So this problem is a convex optimization problem. We can use a generic optimization algorithm to solve that. But this is very slow. And in our previous work, we found that when this kernel has an exponential decay term, when this kernel is an exponential decay function, we have a online algorithm to solve this inverse problem quickly. So here, every time we process one observation at a time, and we sequentially update the spike count. Because when the kernel is like this, it has a very special form, and we only have to update the last spike. The amplitude of the last spike. So it allows us to do online inference of spikes from category quiz. So if you want to do some closed loop experiment, we can collect the data and simultaneously infer the spike count. But if we can also think of this spike inference as a supervised learning task. So given the input, which is a trigonometry, we can use any machine learning models to have an output. So this is if you have the ground truth of the spike count, which can be collected using simultaneously passive imaging and effect recording. So when we have the ground truth, we can train any machine learning model to get the model trained, and when we have the new data set, we can take the fluorescent trace as the input and output the calculated spike count. So several years ago, there is a spike finder computation. They ask different teams to provide their method. So first of all, the spike finder computation provides a list of the benchmark datasets. These datasets are collected with both passive imaging, with the category trees and the spike count information. And so different teams can train their model on these datasets, and they want to figure out which algorithm is the optimal, so that experimental teams can use the selected one. And the result is like this. So different teams, the performance are very similar. They didn't find the optimal strategy. This one, the team 6, the team 6 is the OV6 method I mentioned earlier, which is developed by Johannes, and which is developed by Johannes, is based on the generative approach. So we model the fluorescent trace at the Slowness factor and the kernel. So this one is very simple, and it still performs very good in compared with most neural network deep learning methods. So the next computational command is source extraction. The task is simple: find the neuron location, the RI of each neuron, and also get the temporal trace. Previously, most analysis of most solution for this matter is based on the RI based. RI is the region of the interest. So it's a two-step approach. So first, we can manually or automatically segment the neuron to get the RI, and next we average the fluorescence signal within each RI. So the first, in this part, the second step is very simple. We just take the average of the fluorescence. But the first step is basically a self-segmentation program. So when the data has very high signal-to-noise ratio, you can simply use you can manually segment them. But when you have thousands of neurons, manually segmenting neuron is not possible. Or it takes too long to finish the job. But for if you want to do the computational approach, you can simply do a thresholding and use the watershed to find the boundary, find the barrier between two nearby neurons. But when we do this threshold and watershed, we cannot use the raw frame directly because in each individual frames, only a few neurons are visible. Most of them are not active. In this case, we cannot use the raw frame. So we have to get a summary image first. So we will do the segmentation using a summary image. So we can take the mean image over a long recording. We can also take the maximum intensity projection, or we can compute the standard deviation of the image. But the preferred method is using a local correlation image. The local correlation image is calculated using so for each pixel we have the time phase of that pixel, the red phase here, and it has four neighbors. For neighboring pixel, and each neighboring pixel has their own intensity. So because this pixel is within an RI of a neuron, so it has very large neural signal. In this case, the correlation between the red pixel's activity and its neighbors is very high. But if the pixels within a background, the pixel not within a neuron, the activity of each pixel is dominated by the noise. So the correlation in this case is lower. So with this method, we can compute a very good summary image that is good for self-segmentation. But in this case, the best self-segmentation method is based on deep learning. So in 2015, there is the UNet was proposed, and it achieved the SOTA performance of it achieved the SOTA performance in a self-segmentation computation. And the idea is that you take the raw image as the input, and feed this raw image into a deep learning neural network, and it will output a segmentation. Actually, in the original version, it output the prediction of the ads, the cell ads. And because they have lots of training data sets, so they can use those data sets for training the network. And once the model is trained, you can apply it to the new data set directly. So in this case, if you want to use this self-segmentation approach, the best tool I will recommend is CellPulse. CellPulse was the first version of CellPulse was published in 2021, and now they have CellPulse 2, CellPulse 3, and probably they also have a CellPulse 4. The idea of CellPulse is not predicting this cell boundary. It's they first convert this RI of the neuron into a spatial flow. The center of this flow is the center of the neuron will be the center of this flow. So for each pixel, the flow will go directly to this neuron center. And this will be the training target of the network. So here you have the
Pinwheels.
pinwheels because they have the different directions. For different color represents the different directions developed to the neural center. Neural center, the whole can be built as a soma. So, but this is not soma, but you can this is not a neuron, but yeah, you can think of this as a soma, and the center is just the center of the neuron. How was this calculated? The flow. The flow was just have a very smart way of generating this flow. So this start from a fixed source in the center, and you can think of this as a fixed source, and this source will the page will diffuse outside. You can diffuse one step diffusion, two step diffusion, and you eventually they will get a flow like this. That's no biological chemical something like that. So it's just a computational linear. Oh, so based on RI, they can compute the weighted center. Also compute the flow direction. For example, this is the gradient. This is the gradient in the y direction, and this is the gradient in the x direction. So for this image, you can take the second row subtract the first row, you will get, and the third row subtract the second row. In this equation, you get the gradient. So this is the gradient in the x direction. So you take this row subtract the one row ahead of it. And similarly, you can one column. So if you subtract the column 2 from column 3, you will get the gradient here. Given image can be represented as a function of x, y. No, let me represent the function. Just I
Cannot see from here using cannot see from both.
Oh, okay. So the flow, the gradient is I plus 1 e minus I e this will be the flow the gradient ei is in the x direction. I just consider I plus 1. If then the subtract with the fixed value from this one, you will get the gradient in the x direction as it is. Yes. It's about how to compute this gradient. So once you compute the gradient in the x direction and y direction, this the angle is just it's arctangent. How do I oh I is the image. I is the image. Oh no, the image is generated from this one, from diffusion. They have a very smart way of generating this diffusion image. And you have to have a direct meaning corresponding to technical computation manipulate. It's just a way of generating this output flow from the RI. Given the RI, we generate this output flow. And this flow will be used for computing the relative location and direction of each pixel in relation to the neuron center.
By boundary of
By boundary of the RI.
Yeah, the shape and the specific of the signal. So they have already configured variant in this one. And because they can feature the sometimes will develop this kind of signals. And then you can also retrieve data of the original they have you can treat the elements and this one and how the methods like
So what they have with when they have a branch RI and they generate this gradient in the x direction and the gradient in the y direction. So they will bring a neural network to predict this gradient. And given this network output, they can predict this image, its direction. So at each pixel, you will have the flow going to the neuron center, for example, this one. So for these pixels, they will point to the neuron center. So for each neuron, this direction will point into this neuron center. They have a post-processing method to get the map for each neuron. Mark for each cell. So these are the demonstration of the performance of that code.
How to catch the edge first?
How to get the edge first? They manually label lots of neurons. This is a budget for training. So artificial intelligence starting from from human labeling. So with the samples or your manual labeling, we can get the RI of many neurons. So after we get we have the cell segmentation, we can take the average observations within the RI and get the neurons affected. But is this enough? Maybe not that easy. I will use an example to show you why it's not easy. So here there are two neurons.
Sorry to interrupt. It's always good for the accents and accent.
So the axons and you mean in this matter? I'm not sure whether examples suppose the axons and study. You don't think so? Yeah. I know this matter, but I've never tried it because I have my own method for software experiment. But after we got the results using that representation info, so here there are two neurons, they are close to each other, and the dendrite of this neuron is spatially overlap with another neuron. So if you take the average fluorescence within this RI, it will get contamination from this neuron. So when there are space overlapping between neurons, there are signal contaminations, and this is a problem that has to be solved. And also, we have some background contaminations. So if we take the average within the RI, we didn't subtract the background. But there is a simple background estimation proposed by well, maybe not initially proposed by Maria Castero, but they integrated it into the 3-2P. So the idea is very simple. Given this the RI of this neuron, if you want to activate the background of this within this area, so they first of found some pixels that are not not within the RI of any neuron. So the red pixels, so they are these are the background pixels. There's no neuronal signal. And then take the average. The red pixel is the average of these non-RI pixels, and they use this as a rough background estimation and subtract it from the blue phase, which is the average within the RI. It's not perfect, but it gives a reasonable results. And the other method is called top-hat filter. This is very useful for wide field imaging. So the idea is that we have a neuron here, and you can represent the image patch by representing the pixel value as a hat. So the signal with the existing within this RI has a higher signal. It looks like a hat here, and the background will be this part. So if you want to subtract, so we can just estimate the background using computation local minimum. So you select a small region, for example, you select this region to compute the minimum value within this patch. So probably the minimum value will be here. So this will be very close to the background. But the top filter does another thing. The first comes the minimum value and then compute the maximum value of the minimum. It takes the estimation of the background. So by using this method, using this top hat filter, we can capture the background and get a CNeuro signal. Yes. Okay. So previously we have so quickly summarize the RI-based method is highly dependent on the cell segmentation, and we can roughly subtract the background contamination, but we still didn't solve the problem of we didn't solve the problem of mixing intensity between nearby neurons. So I will propose that, so I will talk about the second approach is called based on matrix factorization. So it's based on a quantitative model of the data. So let's look into the detail. First, so given this raw video data. So the raw video data can be decomposed into multiple terms. So the first term is a neural signal. If neural signal is a combination, is a filter information of all neurons spatial temporal activity. And also a background and some observation mode. So next I will go into the detail of this signal term. So this is the signal of the neurons. We can represent it as a matrix by so this is an image. It's a matrix, and we first we want to move this around. We want to reshape it into a vector. We move the second row here, and move the third second column and the third column here. Essentially, we will represent this image into a vector, and the number of elements in this column vector is d, the pixel number d. And the number of columns is the number of frames. So in this video is another representation of the same video, but we assign a different color for each neuron. And by looking into this neuron, we can further compose its spatial temporal activity into a fixed spatial shape multiplied by the neural activity. That means in each frame, the shape of this neuron doesn't change. But the amplitude, the intensity, the fluorescent intensity of this neuron will change, and it will be captured by this trace. So any questions? How to distinguish different neurons? We haven't done that part yet. Here we just build a model, and when we build a model, we can solve this matrix factorization problem, and we will separate that. Oh, this is only for illustration. This is only for illustration. So therefore, each neuron activity, the spatial kind of activity is decomposed into a neuron shape, which is a column vector multiplied by its sample trace, which is a row vector. And we have mentioned that the neural signal is a superimposition of all neuron spatial kind of activity. So that will be this red column multiplied by this red row, it will give you the spatial time activity of the first neuron. And this green column multiplied by this green column will give you the spatial time activity of the second neuron. So if you convert this superimposition equation, which will be a simple matrix multiplication. We can represent as a multiplication of two matrices. So now we can represent this Y signal as a matrix A multiplied by matrix C. And A will give you the neuron shapes, and C will give you the neural activity. So if you can solve this matrix factorization problem, so given Y, and if we can find A and C, then we will get all neurons location and all neurons activity. I'll skip this part. No. So matrix factorization is a very classical topic in machine learning, and the basic idea is that given this big matrix, you want to represent it as a multiplication of a very tall and thin matrix multiplied by a short and fat matrix. But without constraint, there are lots of combination of this matrix W and matrix A. So we have to add some constraints to make sure that this factorized matrix has the meaning of neuron shape and neuron activity. So in the 2016 neuron paper, activities proposed a constrained didactic matrix factorization program. So they put a lot of constraints into these model variables. First, both the spatial and the temporal components are negative, because we cannot have a neuron shape with a negative value. It's not reasonable. And also for the temporal activity, it's the same thing. We cannot have a negative neural activity. And also the spatial component have a localized and compact footprints. This is only for soma, but if you have a dendrite, we have other constraints. We can add different constraints. And the temporal activity of each neuron obeys the dynamics of Casimir indicator. It's very similar. It's the same as the convolution of the generative model I mentioned earlier in stack inference. For this background term, they also use a low rank matrix to approximate the background. This works well for the two photon image set, but not for one photon. I will explain that later. Any questions? Okay. So given these constraints, and observe the data Y, we can do a matrix factorization to get A and C. So. And these are some demonstration of A. A gives you the neuron shape. These are the C term, which is the neuron activity. And this model is very flexible. So sometimes when you do the matrix factorization, you may split one neuron into multiple components, and then you can merge these components into one by fitting the model again. So after Aptitude's proposed CNMF, it was widely adopted in the field, and the most two-photon Pengcheng data were processed using this method. In the meantime, there are another popular imaging technique is the microendoscope. The microendoscope uses mid-H microscope to mount it on the animal's head, so that because it's very light, it's very small, and it's very light, the animal can really behave while carrying this microscope. But the data looks like this. It has very light background contamination, and we can barely see neurons activity. So if we still want to use this matrix factorization framework, so we can do the same thing by adding constraint to the neuron trace and the neuron trace. So magneticity, sparsity, spatial compactness. We can do the same thing, but for the background term, it's the main trouble because the background fluctuation is much bigger than the neural signals, and this background term is not cannot be simply modeled as a low rank matrix. And even actually it can be modeled as a low rank matrix, but without proper constraints, you cannot separate them. Once you make any error in this background estimation, the error will go in. The error goes into the estimation of the neural signal. So that's the main trouble of directly applying CNMF to this one photon image dataset. So I started working on this dataset, and after looking at the data for a long time, I figured out I first started thinking about the source of this background. So the background has some local background, which this is due to the blurring effect. It's very localized, and also has some blood vessels. And global background is related to the illumination. And also in the raw data we get a neuron signal. So by looking at this signal source, I think about how can I propose a method to separate the neuron signals from the background. And eventually I found that the background sources have a larger spatial range than the neuron. And based on this one, I proposed a simple ring model. So given each pixel, I select some neighboring pixels with a distance of L. And this L is to be carefully selected. It should be larger than a neuron. It should be larger than a neuron. So in this way, we can make sure that the center pixel and this neighbor pixel on the screen, they should not belong to the same neuron. That means the distance between this pixel and this pixel are larger than a neuron size. So they don't share the signal from the same neuron, but they share the same signal from the background source. So if they share the same background source, I can do a linear combination of this linear combination of active fluorescence on these pixels to reconstruct the background here. So the formula is like this. So G is the pixel, is the index of pixel index on the screen, and by computing a weight of WIG, we can reconstruct the background in the center. So in this way, we can only reconstruct the background, but we cannot reconstruct the neural signal. This is the case. So once we see this linear regression problem, we get WIG hat, and then we can reconstruct the background. So with this very simple method, we can estimate this background. If we subtract this estimated background, we can see very clear neural signal here. So when after we started after we proposed this method, we have some collaborations, and we have a collaborator who are studying the stratum using this miniature rat microscope. So in a previous research, they did so these two groups are doing the same experiment. They want to the scientific question is what's the spatial organization of the temporally correlated stratum neurons, because these neurons encode some motion-related information. They want to see if neurons include the similar information, are they spatially compact, spatially close, something like that. And in an earlier paper, in neuron paper, they reported that neurons encode the similar information. They are spatially compact. They form a spatially compact neural clusters. But our collaborators using our method, they found that neurons encode similar behavior motion information. They are not spatially they're spatially close, but not form a spatial cluster. And so two neuron paper, they using the same experiment, but got different results. Why? And so our collaborator found that we use a simulation, and we found that the earlier paper using local background and baseline collection RBC method. The RBC method is very similar to the one I mentioned in the earlier. It's proposed by Marius Pengcheng in Sweden to keep. We choose the annular region and we drop the estimated background using the average observation within this blue area, blue ring, and the subtracted from the lesion activity in the center. So because we have a simulation, we have the ground truth, and we use our method and this method. We can see that using RBC method, the extracted neural signals are contaminated by the background. So nearby neurons will have superior higher time correlation because of the background. You didn't subtract the background correctly. Then you get this higher correlation because of the common background signal. And also here we show that using our method we can predict the spatially close neuron activity. Using a previous method, when this neuron has a high spike activity, there is a negative spike here. This negative spike here. And then there's a link of the neuron activity from this neuron to this neuron. But our method can solve this problem.
Maybe we can take
a short break. Okay.
Break, 5 minutes.
5 minutes. Okay. Okay, let's move to the next section is about motion fraction. So we developed the CMF and the CMFE, but a lot of users are using it, and I got lots of questions about do you have a method for motion fraction? The answer is no. So we always assume that data have been motion corrected, but this is but sometimes for most data set it's not easy to do motion correction. We have a new method to do motion correction very good, but I didn't include them into this lecture. So I will only review the quickly review the basic idea of doing motion correction in existing method. But if you have in your own lab, if you have trouble in applying motion correction to your data set, probably you can send me an email and test our new method. So motion, there are two types of motion. One is the rigid motion. The only shift only shift or rotate, but this image doesn't there's no warping, there's no distortion, just a shift in XY direction. So this rigid motion correction is very easy to do. This is the original image, and this is yeah. If you look at it, you are in this direction, and we just this image with some dot x and dot y. The correlation between these two images will be changed as well, and this correlation coefficient will only be the maximum perfectly aligned. So the math, if they have perfect alignment, then they have the best match. They have the best correlation coefficient. But if you shift in any direction, this correlation coefficient will decay, and if you probably this correlation coefficient may be close to zero. So the idea of doing motion practice, doing rigid motion practice is just computing this cross correlation image. This cross correlation image is very simple. So if you shift this image in with the different combination of x0 and y0, so you shift in here, that's no shift, you compute the correlation coefficient, and if you shift in x direction, get a new pair of x0 and y0. You compute the correlation coefficient again. By computing a lot of combination of x0 and y0, you get this cross correlation image. And by looking at this cross correlation image, you will have a shift here. That means when you shift a second image with this x0 and y0, they achieve the best match. So when it achieves the best match, that means you have found a solution of this rigid motion factor. So this is the basic idea of doing rigid motion correction. But when we image most field of view, we have a very large field of view. Rigid motion correction. This data can have some non-rigid motion in some case. And we couldn't use this approach. We couldn't simply use this approach. But the idea of doing non-rigid motion correction is by doing a piecewise rigid motion correction. The idea is that into multiple small patches. And we assume this patch will be within this small patch. There is only rigid motion correction. So within this small patch, there is only a motion vector. But different patches have different motion vector. Then we can get that rigid motion. Any questions? if they move different direction, you mean different patches that move in different direction. Yes. Yeah, because in this case they will have an overlap of the patches. So within this overlapping area, they take the average. Take the average.
Separate problem, though some video cameras have a rolling shutter where the different lines are actually not acquired at the same time.
Okay.
So that you almost have to do a separate direction for the lines.
Well, I have those kind of data, but I don't know about it.
Depending on the model of CCP, the frame may not be synchronous.
Yeah. Well, I don't know about that program. Okay. Good question. By experience. They will roughly look at they will roughly look at the data set, and they will estimate how serious of this language motion. If it's not very serious, they use very large image patches like this. But if you are not happy with this result, you can further reduce the size of the patch like this one. So basically, you start from a big patch and get the result. If you are not happy about that, then to reduce the patch size.
Okay. So how about when there is some minor movement in the Z?
In this direction, I don't have a solution. I don't think we can get a good solution for that one unless you use some machine learning, some AI method to make a good get. Because you lock the information completely this action.
Of course, if you move too much, completely all of poker.
Yeah, you already have to with maybe. So the next section about the video denoising. This is very powerful too. How many of you have used the deep interpolation or deep CAD before? No? What? It's very powerful. You should try it. Although they are not proposed in our lab, but I still like it. So if you look at this video, it's very noisy. You can barely see the nuance shape, and if you take the average between this area, it looks like this. That's noise, and for the small fact, the small fact activities, you can suddenly discriminate them from the background. So what if you can do video denoising? This is the result of the video. If you do the video denoising. First of all, you can see this nuance queries. If you really want to do manual segmentation, then manually segment this nuance will be much easier. And if you take the average information, the time period is segmentation. With also the result, this is the rolling, and this is the deep field influence. So to keep the speed, the speed of data processing. The speed of what? The process. I don't know. Because I developed my own method. I didn't try it, but my students tried it. It's kind of slow, but at a reasonable time. If you have a good GPU, then the speed is okay. But we have our own version that can do simultaneously motion correction and denoising. If you process 100 frames, it's like 50 seconds. Oh no, sorry. 1 second for 100 frames. it can achieve a real-time motion correction and denoise in our case. But my results were not shown here. The good part of this matter is that you don't need a ground truth. You only need to provide the raw data set. Provide the raw data set, then you can create a neural network, and the neural network will output a video like this. If they process the raw data using this method, we can achieve better source extraction with it. So if you process the raw data, if you do source extraction from the raw data, there are lots of this missing. Their signal are not strong enough. The existing source extraction method may miss these neurons, but if we pre-process the data with deep CAD, we can find most of them. So what's the magic behind deep CAD is loss to noise. It's the idea proposed in the artificial intelligence community. Because given that a neural network is very powerful, it's a very powerful function, can do a lot of things. If you have the one input and a clean target, then we can train this network. So once this network was trained, you can process other noisy images. But in reality, in our case, is that we don't have the ground truth. So we want to denoise the broadcasting image data, but we don't have the ground truth. If we don't have the ground truth, we cannot train this model. That's a naive idea, which is not true. Even though we don't have the ground truth, we can still train the model. The idea is not to noise. Even though we don't have the ground truth, we can use a noisy target to supervise us. To supervise us to train this network. Why? There are some reasons. So this network is a function of theta. Theta is the weight of the parameters, the network parameters. But that's the input of the it takes a noisy image as the input, and this noisy image is a plain image plus noise, plus N1. And if you have the plain signal as a target, the training the model is to minimize the difference between the network output and the plain target. But if you don't have this X, then but if we don't have this target, but we replace this target as another noisy image, it shares the same plain image, but it's noise. This is another image. So this image has the same target as the image 1, but it has different noise and 2. So now we replace this plain image with the X plus N1 to noise image. And this other mean is that we want to minimize theta. We want to optimize theta to minimize spectrum. And we can rewrite this term into this one. And in this case, so this one is the same, but this term N2, the noise, is a constant. And it's not dependent on theta. So when we optimize this theta, this term has no effect. So in this case, the optimization of this, the optimization proportion of this one is the same as fitting with the plain target. Expected?
Simple. The two nodes are actually the same. So you can so N2 is equal to N1.
Okay, let us show the magic truth. Actually, it's an assumption. We only have one frame. Right? In the equation, we only have one frame for we only have one frame. So they make another assumption that the nearby frame.
I'm sorry.
No, they assume that the nearby frame is the same. So the frame 1 frame 1 is the same as frame 2, frame 3 is the same as frame 4. Because of the because of the slow calcium dynamics, frame 1 and frame 2 they have no big difference because they never close to each other. So here the input will be accumulated of multiple frames, basically all the frames, and the output is the training target is the even frames. 1, 3, 5, 7, 9, and they assume that these 5 frames have the same clean signal as the frame 2, 4, 6, 8, and 2. It's an assumption, it's not perfect assumption.
So the only noise source that's different is electronic pixel noise?
That's a good question. So this not only the pixel. I would say that those nodes are independent between two frames. But what are the source of those noises? I'm not sure. There are some fluctuations in the recording. So I have your question that those noises are from the CCD.
Did you know that this was capital noise? For the traffic methods.
I think the only I think it's not only one type of node. It's just something that as long as this confirms don't share the same don't share the signals that are not shared between these frames, then the power will not.
Well, the question is, what is that?
We don't know. It's just something that we cannot explain. Something that cannot be explained in this raw signal. In this clean signal. Something other than a clean signal. So, there's another deep learning method for doing denoising. It's called deep interpolation. So idea is very simple as this one. They still train. They also train the network using noise image. They don't need clean quantum. But the idea is like this. So it's based on interpolation. So you can take this term up, and because of the temporal correlation, some redundancy in the neural activity, we can interpolate this frame using grounding frames, 10 frames before, 10 frames after. But we have these frames, we can interpolate the middle frame. Right? So we will take this frame off and take the surrounding frames as an input, and they still pass them into a network. And the network will output the interpolation. Will output interpolation, and the training target will be this center frame. Yeah, that is, we can only interpolate neural signals, but we cannot interpolate the noise in that center frame. That's the same as the previous node idea. So once so they will compute the loss between the network output and the center frame. And once the network is trained, you can use a shifting window to know each frame one by one. Any questions?
Yeah. So for video denoising and the motion correction, which step should be done first?
Which one?
Which one should be done first, and which is second?
That's a great question. Well, I should include that part maybe into my next lecture. Include that into my next lecture, but I can quickly for this one you have to do motion correction first. But here's the tricky part. If you aim for low signal to noise ratio, motion correction, the performance of motion correction is bad. Because when we do motion correction, highly depends on this correlation image. When the signal, when the noise is too high, the correlation coefficient will be dominated by the noise instead of the neural signal. So when the signal to noise ratio is too low, motion factor is degraded. The performance of the motion factor is degraded as well. But we have a method of solving this problem. I would recommend you to try integration because I talked with a member Jamie Wu, who is in the same lab as the inventor of the deep CAD, and told me that there may be some artifact in this deep CAD. Okay, so I think it is deep integration effect. Okay, that's enough. So the last topic is about multi-section registration. If we do, if we're recording the same population neuron over many days, here like 6 days, and we can extract this neuron spatial neuron RI for each section individually. And the next step is to register this neuron to make sure that all these neurons will have the same ID so that we can track the functional property of each neuron. For example, this is an example of application this is an example inserting in hippocampus. And they do recording over a subtype days, and they data the split field of individual neurons. So they can evaluate the consistency of the split field of each neuron. So, but the cell registration is a non-trivial problem. Why? There are three reasons. First, the most important part is the change of the field of view. If you record the same field of view over a long section, over multiple days, the field of view will be distorted due to some unknown reason. Well, I'm sorry, you all know the reason, but I don't know because I'm not experiment on your side. Usually the field of view is spatially warped. If the field of view is spatially warped, if you overlap section 2 neuron with the section 1 neuron, they don't have a they don't have a perfect match in the spatial location. And also some neurons will have a slight change, some slight change of the neuron shape, and some neurons will disappear in some sections. For example, the red neuron this red neuron is not visible in section 2, but this in section 2 there's a new neuron is the green neuron here, that's a new neuron. So the strategy of previous work is that it involves 2 steps. First, we have to do a FOV alignment. First, we have to do image registration. We have to align the field of view in section 2 relative to the FOV of section 1. And once they are aligned, we can set some threshold. For determine whether these 2 neurons are matched or not. For example, if a neuron if 2 neurons are matched, they should have a small spatial distance and a high shape correlation. But the trouble is here, the FOV alignment is not easy. It's not easy for many reasons, and I will just talk about them now. I will just propose my approach for solving this self-registration problem. The idea is based on a point set registration problem in computer science community. So given the 2 point sets, the red one and the green one, the point PSR problem is to find the correspondence of the red dot and the blue dot. by finding a spatial warping field. This spatial warping field should be smooth. So in that two things, you have to find a spatial warping field, which is a transformation of this coordinate. Find a spatial transformation and also find the identity mapping. So this is exactly the thing we want to do in cell matching, in cell registration. So here, okay, let's start. So at the beginning, we have a set of red neurons and a set of green neurons, and we want to find a spatial warping to try to align these red neurons, try to align these green neurons with the red one. This is the result. So we use an iterative optimization approach to solve this problem. So we iteratively find a spatial warping. You can see that we're refining our spatial warping function, and this part is showing the matching probability of two neurons. At the beginning, each neuron has multiple options. But as we refine this spatial warping function, we're more sure about the exact match. You can see that. Any questions? No. And this Factor-Centric registration method is very good in handling 3D data sets. If you do a volumetric imaging, doing a 3D FOV alignment is hard, but here we only need to know the neuron location. And solving this PSR problem is much easier in this case. So we can avoid the hard FOV alignment problem. Okay. We also apply this method to real neuron data set. So you only need to provide the individual neurons RI, and it will find the spatial warping and the correspondence. If you can see this dot, so this dot indicates the match of the neuron in this set and the neuron in this set. Okay. At the end of my talk, I want to steal a slide from my postdoc advisor in chemistry. It said that it's a golden age for statistical neuroscience or neural data science. So these days we have very fast, cheap computation. We have a lot of statistical machine learning methods and also artificial intelligence methods. In the meanwhile, we have the best data set in neuroscience, optical genetics, and also electrophysiology. We have very large scale data sets. But more importantly, we have to develop new scientific directions. So because many fundamental neuroscience questions are statistical problems in this case. So we have to build a close collaboration between experimental neuroscientists and computer scientists, physicists, or people from the quantitative background. They have nice discussions and formulate neuroscience problems into some computational tractable problems. Okay, that's my talk. Thank you.